Hello and welcome to The Sleepy Scientist. It is lovely to have you here. Before we begin, I would love to know where in the world you're watching from tonight. Maybe you're lying in a quiet bedroom, lights low and blankets pulled up. Maybe you're on a drowsy train ride, watching stations drift past in the dark. Or perhaps you are curled up on a cozy sofa with a warm drink in your hands. Wherever you are, I hope you feel calm, unhurried, and ready to wander gently into thought. If you enjoy these calm explorations and would like to hear more, a like and a subscribe really helps this sleepy little channel keep floating along. And to those of you who are already subscribed, thank you. Truly, your support means more than you might realize. Now, I will try not to make tonight's topic so interesting that it keeps you wide awake, but if it does, at least you may drift off with a slightly clearer sense of why the mind feels so mysterious and why some people think it might be entangled with the strange rules of the quantum world. A small price to pay for a restless night. So shall we begin? What is quantum consciousness? And why does it sound as though your thoughts might be brushing up against the deepest uncertainties in physics? The world you know, the one you can see and touch every day, feels solid and steady. When you put a cup on a table, it stays there. When you walk across a room, the floor does not vanish under your feet. The sun rises, the sun sets, and the ordinary rhythm of a life rolls on without asking too many questions about how any of it is experienced from the inside. But over the last century or so, scientists began to look at reality in two very different ways. On one side, they examined the outer world of matter, peeling it back layer by layer until they reached the tiny, jittery realm of quantum physics, where particles can behave like waves, where they can exist in many possible states at once, and where the simple act of measuring them seems to change what they become. On the other side, they turned inward, toward the inner world of awareness, asking what it really means to be conscious, to feel, to see, to experience anything at all. The more closely they studied each world, the stranger the questions became. In the quantum realm, events are not always fixed and certain. They live in clouds of possibility until something selects an outcome. In the realm of the mind, experience is private and vivid, yet built from the activity of billions of tiny cells. Somewhere between these two mysteries, an idea began to grow. Could consciousness and quantum physics be linked? For some, this suggestion is thrilling. It hints that your awareness might somehow be tied to the deepest workings of the universe, that thoughts and perceptions might be woven from quantum threads. For others, it is a step too far, mixing speculation with science in a way that needs to be handled very carefully. What most people agree on, though, is that both consciousness and quantum mechanics are strange enough on their own to deserve a slow, gentle look. In this video, we will drift quietly through that possibility. There is no need to memorize theories or master equations. We will move slowly, one idea at a time, asking what consciousness is, what quantum physics really says, and where, if anywhere, the two might honestly meet. From the familiar solidity of everyday life, to the shimmering probabilities of the quantum world, to the quiet sense of being you behind your eyes, we will explore how far science can go, and where the mystery remains. So tuck yourself in, close your eyes if you would like, and let your thoughts loosen just a little. Let us begin to explore a world where particles can linger between possibilities, where observation seems to matter in subtle ways, and where the simple fact that you're aware may be one of the most remarkable things the universe has ever done. The phrase quantum consciousness sounds almost like a riddle whispered by the universe. It brings together two of the deepest mysteries we know, the strange behavior of matter at its smallest scales, and the vivid, private feeling of being aware. Each of these topics is already puzzling on its own, but when they are placed side by side, they create a question that can feel both thrilling and unsettling. What does it actually mean for consciousness to be quantum? And why has this idea captured so much attention, even though science has not reached a firm answer? To begin gently, quantum consciousness is not a single theory. It is a family of possibilities, all centered around one simple idea. Perhaps the mind works the way it does because some of its processes rely on the unusual rules that govern the quantum world. Those rules include superposition, where something can exist in several possible states until a measurement is made. They also include entanglement, where two particles can remain mysteriously linked no matter how far apart they drift, and uncertainty, where the exact behavior of something cannot always be predicted with perfect accuracy. These ideas do not behave like the daily world you move through. They are delicate, unpredictable, and full of possibility. And some researchers have wondered whether consciousness might share qualities with them. But it is important to say this slowly and calmly. Quantum consciousness does not claim that thoughts are made of particles doing impossible tricks. It does not claim that your awareness is floating in a cloud of probability. Instead, it suggests something more measured. It asks whether the brain's immense complexity could make room for tiny quantum effects that influence how information is processed, or perhaps how awareness arises. It asks whether some features of consciousness might only make sense when viewed through a quantum lens, just as some features of matter only make sense when viewed at quantum scales. This idea rests at a crossroads where physics, neuroscience, and philosophy gently overlap. Neuroscience studies how neurons fire, how memories form, and how perception takes shape in the brain. Physics studies the building blocks of reality and the laws that guide them. Philosophy tries to understand the nature of experience, the meaning of awareness, and the structure of reality itself. When all three fields focus on the same question, the result is something that feels larger than any one discipline. It becomes a careful conversation between inner life and outer world, between what the mind feels like from within and what matter behaves like from without. A calm way to imagine this is to picture the mind as an ocean and the quantum world as the grains of sand on its floor. The ocean feels vast, fluid, continuous. Waves rise and fall, thoughts drift like currents, memories shimmer beneath the surface, but underneath everything, tiny particles sit at the foundation, each governed by rules that defy intuition. The question of quantum consciousness is not whether the ocean is made of quantum tricks. It asks whether those tiny grains, behaving in their strange and delicate ways, might subtly shape how the ocean moves. Another helpful metaphor is to think of the mind as a lantern glowing on a still night. The lantern represents the feeling of being aware, warm and steady. But the flame inside flickers in patterns that depend on fuel, air, and movement. In the same way, consciousness may feel smooth and unified, even if its inner workings include 1,000 microscopic processes interacting in ways we do not yet fully understand. The puzzle is whether some of those flickers might follow quantum principles rather than classical ones. There is a reason this idea can feel both exciting and controversial. On the one hand, quantum mechanics describes nature at its most fundamental level. Since everything is ultimately made of atoms and atoms obey quantum rules, it is tempting to imagine that consciousness could be deeply quantum as well. After all, the brain is built from the same tiny pieces of reality as everything else. On the other hand, the brain is warm, noisy, and full of constant activity. Quantum effects normally thrive in quiet, controlled environments. They are fragile. They can be disrupted by the slightest disturbance. The brain, by comparison, is more like a lively marketplace than a serene laboratory. Many scientists believe this makes quantum effects unlikely to survive long enough to influence conscious thought. Others believe the brain may contain pockets of structure capable of protecting quantum behavior in surprising ways. So quantum consciousness lives in a gentle space between possibility and uncertainty. It is neither proven nor disproven, neither embraced nor dismissed. Scientists continue to explore whether quantum processes might play a role in perception, decision-making, or the sense of self. They examine molecules inside neurons, the structure of cellular scaffolding, and the timing of electrical signals, searching for hints that the quantum realm might be quietly shaping the mind. At the same time, philosophers look at awareness from the inside and wonder whether its richness, its subjectivity, its immediate presence could require something more than classical explanations. The importance of this idea does not lie in claiming that quantum physics explains consciousness. Instead, its value comes from the questions it encourages us to ask. It invites a softer view of the mind, one that embraces mystery as part of the journey. It reminds us that the brain, for all its mapping and measurement, still holds secrets. It nudges us to consider whether reality is more intertwined than it appears, and whether the boundary between observer and world is thinner than we assume. When approached slowly and without exaggeration, quantum consciousness becomes less of a grand statement and more of an invitation. It invites curiosity. It invites wonder. It invites the possibility that the smallest scales of nature and the deepest layers of the mind might be connected in ways we're only beginning to imagine. Even if quantum effects prove not to be the key to consciousness, the exploration itself opens doors. It encourages new perspectives on thinking, awareness, and the structure of experience. And so this chapter begins with gentle clarity. Quantum consciousness may or may not describe the true workings of the mind, but it does offer a way to hold two mysteries in the same thought. The quantum world, with its fragile beauty and endless possibility, stretches downward into the heart of matter. Consciousness, with its shifting feelings and vivid presence, stretches inward into the heart of experience. Between them lies a question worth drifting through with patience, a question that sets the stage for a calm and curious journey into how the universe behaves at its tiniest scales and how the mind finds its glow within it. Quantum physics is one of those subjects that sounds intimidating until you realize it is simply describing how the universe behaves when everything is very, very small. Not small like a grain of sand or a dust mote floating through a sunbeam, but small in a way the mind can hardly picture. At these tiny scales, the familiar rules of everyday life quietly loosen, and new rules take their place, rules that can feel dreamlike or even mischievous. And yet they are real, measured again and again, consistent enough to form the backbone of modern technology. To understand quantum consciousness, it helps to first understand what makes something quantum in the first place. A gentle place to begin is with the idea of superposition. In the everyday world, things behave in tidy, predictable ways. A light switch is either on or off. A coin lands on heads or tails. A cat, one hopes, is either inside the room or outside it. But in the quantum world, things are allowed to exist in several possible states at once. A particle does not choose one position, or one path, or one energy level immediately. Instead, it drifts through a haze of possibilities until something interacts with it. Only then does it settle on a single, definite outcome. A soft way to picture this is to imagine the universe giving each tiny particle a handful of possible futures, letting them shimmer softly beside one another until the moment a choice must be made. Another gentle mystery is entanglement, a behavior so unusual it once prompted worried letters between some of the most brilliant physicists of the early 20th century. When two particles become entangled, their states intertwine in a way that remains connected regardless of distance. If you imagine two birds flying off in opposite directions yet somehow always turning together in perfect synchrony, you would not be far from the truth. Changing something about one particle tells you something about the other instantly, even if they are separated by a stretch of space that would take years to cross at the speed of light. This does not allow communication faster than light, nor does it break the universe. It simply reveals that the quantum world does not always respect the boundaries our intuition expects. Then there is uncertainty, which might be the most misunderstood idea of all. Quantum uncertainty does not mean we are confused or that our tools are clumsy. It is a built-in feature of reality. At very small scales, certain properties cannot be known perfectly at the same time. You can picture this like trying to hold a soap bubble exactly still while also measuring its exact shape. The more precisely you try to pin down one detail, the more another squirms away. This is not a flaw in measurement, but a reflection of how nature behaves. Tiny particles do not have fully defined properties until interactions give them form. All of this raises a gentle question. Why do these strange rules not show up in daily life? Why does your morning teacup not drift through a haze of superposed positions as you reach for it? The quiet answer lies in size and connection. Quantum effects thrive when things are isolated, tiny and undisturbed. At small scales, particles are so light and so delicately balanced that the universe's usual rules soften, allowing possibility to bloom. But in the world you can see and touch, everything is enormous from a quantum perspective. Objects contain trillions of particles interacting constantly with one another and with the environment. Those interactions wash away quantum behavior almost instantly, a process known as decoherence. It is as though the world's noise is too loud for quantum subtlety to survive for long. This is why quantum effects dominate the microscopic realm. Electrons, photons, and other tiny particles are small enough to slip beneath the roar of everyday physics. They drift and shimmer in states of potential. They dance through a world where probability replaces certainty. It is only when they gather into large objects or interact strongly with their surroundings that the familiar solidity of classical physics reasserts itself. But even with these rules, quantum physics is often surrounded by misconceptions. One common misunderstanding is that superposition means a particle is literally in many places at once. A gentler, more accurate way to picture it is as a cloud of possibilities. The particle can take many paths or hold many states, but those possibilities exist as mathematical descriptions of what could happen, not a physical swarm of miniature duplicates. Another misconception is that consciousness must be involved in observation. In physics, observation simply means interaction. A particle bumping into another particle or being scattered by a beam of light counts as a measurement. No conscious mind is required. The universe does not wait for someone to look at it before behaving. There is also a tendency to view the quantum world as chaotic or mystical, as though it refuses to follow any rules at all. In truth, quantum physics is one of the most precise and successful frameworks ever developed. Its predictions have matched experiments with extraordinary accuracy again and again. The strangeness is not a sign of confusion. It is a sign that reality at its smallest scales follows patterns that do not resemble the patterns of everyday life. A soft way to imagine this difference is to picture the universe as a calm lake. On the surface you see smooth waves, drifting leaves, gentle reflections. This is the everyday world, steady and familiar, but beneath the surface lies a hidden world of currents and eddies, tiny movements and shimmering details. The water molecules dance in ways that are far too small for the eye to notice. These movements shape the surface in subtle ways, but they follow rules of their own. Quantum physics describes the hidden dance beneath the visible lake, while classical physics describes the waves you can see. Another metaphor is to imagine a library with two kinds of books. The large books, bound in thick covers, represent the classical world, filled with clear sentences and straightforward stories. The tiny books, barely larger than a matchbox, represent the quantum world, full of poetry, possibilities, and lines that change each time you read them. Both libraries are essential. Both describe the same universe. They simply tell the story at different scales. Understanding what makes something quantum sets the foundation for exploring deeper questions. Once you see how particles behave before they form larger structures, it becomes easier to imagine why some scientists wonder whether the brain might host its own tiny quantum processes. The brain, after all, is a place of immense complexity. Within its cells are molecular structures arranged with extraordinary precision. Whether those structures protect or amplify quantum behavior is an open question, one that inspires both enthusiasm and caution. But before considering those possibilities, it helps to rest in the knowledge that quantum physics is not magic. It is simply another layer of reality, one that becomes visible when we look closely enough. It offers rules that feel unfamiliar but consistent. It shapes the building blocks of atoms, the behavior of light, and the patterns that allow matter to exist at all. It is the quiet machinery beneath everything you experience. By approaching these ideas slowly, they lose their harsh edges. Superposition becomes a soft cloud of maybes. Entanglement becomes a gentle link between distant partners. Uncertainty becomes a reminder that some details of nature settle only when they must. And the quantum world becomes less of a puzzle and more of a delicate, shimmering foundation upon which the familiar universe rests. With this understanding, the mind is better prepared to explore how these small, whispering processes might relate to awareness itself. Whether or not consciousness draws upon quantum mechanics, the ideas that shape the quantum world help us appreciate just how strange and wonderful the universe can be when we look closely. Consciousness is one of those ideas that feels completely obvious until you try to explain it. You can point to a cup on the table, you can recall a memory from childhood, you can feel the warmth of a blanket or the sharpness of a lemon slice, and all of this seems straightforward. You are conscious, so you experience things. Yet the moment you try to define what consciousness truly is, the ground beneath the idea begins to shift. It becomes slippery, subtle, and layered, as if the mind is trying to look at itself from the inside and discovering that mirrors do not work the same way in here. Scientists often begin with simple definitions. Consciousness is the state of being aware. It is the ability to experience sensations, thoughts, and emotions. It is what allows you to notice the color of the sky, to hear the hum of a distant car, to recognize your own reflection, and to feel the steady presence of your own inner life. Awareness is at the center of this definition, but awareness itself has many forms. You can be awake and fully alert. You can be daydreaming. You can be drowsy, drifting in the space between thoughts. You can even be dreaming, where the mind invents a world without consulting the real one. Consciousness is the thread that runs through all these states, connecting them into a continuous sense of being. Another way to understand consciousness is through perception. Perception is not just receiving information from the world, it is shaping that information into something meaningful. When you see a cup, you are not seeing raw light hitting your eyes. You're seeing the brain's interpretation of shape, color, depth, and context. You're seeing a story the brain has assembled. Perception filters, edits, interprets. It constructs a world that feels stable and rich, even though the raw information arriving from the senses is messy and incomplete. Consciousness is what it feels like to inhabit that constructed world with all its detail and texture. Then there is subjective experience, sometimes called the inner perspective. This is the most mysterious part of all. It is the part of consciousness that includes the feeling of tasting something sweet, of hearing music that gives you chills, of noticing the coolness of air on your skin, or the presence of a thought forming in your mind. It is the sense of being someone, a point of view that exists inside a body looking outward. Scientists can measure brain activity, track neural pathways, map sensory regions, and observe electrical rhythms, but they cannot directly access this inner feeling. They can see the brain light up when you look at a flower, but not the colour you experience. They can measure the processes involved in memory, but not what the remembered moment feels like from within. This gap between the physical workings of the brain and the inner experience of consciousness is one of the main reasons it remains so difficult to explain. On one side, there is a vast body of knowledge about neurons, synapses, chemicals, and impulses. On the other side, there is the undeniable fact that being conscious feels like something. Bridging these two sides is one of the great challenges in science. How does a physical system made of cells and molecules produce subjective experience? How does electrical activity become a feeling? How does a biological machine generate the sense of being alive from the inside? The mind has been puzzling over these questions for a long time, and sometimes it almost seems amused by its own confusion. After all, the brain is trying to use itself to understand itself, which is a bit like a book trying to read its own pages. It is impressive that the brain can do it at all. A little humour helps here. You can imagine neurons throwing up their hands and saying they never signed up for philosophical duties. They were perfectly happy sending signals and forming networks, and suddenly they are being asked to explain the nature of subjective experience. It is no wonder the answers take a while. Still, scientists do have ways of studying consciousness. One approach is to examine levels of awareness. The brain behaves differently when awake, asleep, dreaming, or in states such as anesthesia. These differences help reveal which networks contribute to conscious experience. Another approach looks at the integration of information. The idea is that consciousness may arise when information is not just processed, but woven together across many areas of the brain. When sights, sounds, memories, and emotions flow together into a unified picture, awareness emerges. This does not solve the whole puzzle, but it helps describe the conditions under which consciousness seems to flourish. Some researchers focus on the content of consciousness. They study how attention shapes what you notice, how the brain selects which information rises to awareness and which remains in the background. They look at how perception can be fooled by illusions, showing how the brain actively constructs its version of reality. All of this points to consciousness as something dynamic, flexible, and deeply connected to how the brain interprets the world. Despite these insights, there is still no universal agreement on what consciousness fundamentally is. Some define it in terms of behavior. If an organism can respond to its environment in flexible ways, it might be considered conscious. Others focus on the inner experience, arguing that without subjective feeling, consciousness is incomplete. Some see consciousness as emerging from complex networks. Others believe it may require new physics entirely. The diversity of views reflects the complexity of the topic. One gentle way to imagine consciousness is to think of it as a lantern glowing in a quiet room. The lantern does not create the room, but it illuminates it, revealing shapes and shadows. The light inside the lantern is shaped by what fuels it, by the glass that surrounds it, by the air drifting through it. In the same way, consciousness illuminates your inner world. It reveals memories, emotions, sensations, and thoughts. It does not create them, but it lights them up, making them available to experience. Another calming metaphor is to imagine consciousness as the surface of a lake. Beneath the surface lie currents of memory, instinct, and perception. Above the surface lies the wider world, full of sounds and shapes. Consciousness is the meeting point between these two realms, where inner and outer worlds blend into a single moment of awareness. The surface shifts with the weather, with time of day, with mood. But it always reflects something. The difficulty in explaining consciousness arises partly because it is both familiar and hidden. Everyone experiences consciousness directly, yet that experience cannot be shared or measured in the same way as other scientific data. You can hold a microscope to a cell or measure the distance between stars, but you cannot place someone's subjective feeling on a scale. This makes consciousness both deeply personal and scientifically elusive. It's also difficult because consciousness feels unified, even though the brain is made of countless parts working simultaneously. Vision happens in one region, hearing in another, decision-making in another. Yet your experience knots them together into a single thread. You do not feel separate processes, you feel one continuous flow. Understanding how this unity arises is one of the central puzzles of consciousness research. All of these complexities help explain why consciousness is so hard to pin down, even though it underlies every moment of your life. It is the backdrop against which everything else happens. Without consciousness, there would be no thoughts to think, no memories to remember, no world to perceive. And that brings us to a gentle but important point. Before exploring whether quantum processes play any role in consciousness, it helps to appreciate the richness of the phenomenon itself. The mind is vast. Experience is layered. Awareness is deep, fluid, and shaped by countless factors. The study of consciousness is not just the study of neurons or cells, it is the study of what it means to be aware at all. It is the attempt to understand the glow behind your thoughts, the feeling of looking out from behind your own eyes, the subtle shift between wakefulness and dreaming. When approached softly, without pressure for grand conclusions, consciousness becomes a landscape worth wandering in its own right. Whether or not quantum physics contributes to this landscape, the essence of consciousness remains one of the most beautiful mysteries in nature. It is the quiet presence behind every sensation, the gentle witness to your own existence, and the inner light that makes every moment feel alive. When scientists talk about the brain, they almost always begin with classical physics, not quantum physics. This is not because the quantum world is unimportant, but because the brain is such a large, warm and electrically busy environment that classical explanations are usually more than enough to describe how it works. In everyday neuroscience, the brain behaves like a biological machine built from cells, chemicals, and electrical pulses. It does not need delicate quantum states to function. It relies instead on reliable physical processes that can be measured, predicted, and observed again and again. Before drifting into ideas about quantum contributions to the mind, it helps to settle into this classical picture, the one that has shaped neuroscience for more than a century. A useful starting point is the neuron, the basic working unit of the brain. Neurons are specialized cells that send and receive signals. Each neuron has a cell body, branching dendrites that receive information, and a long axon that carries signals to other cells. When a neuron becomes active, it generates an electrical impulse that travels down the axon like a tiny wave. This wave is not mysterious. It follows classical rules. It depends on the movement of charged particles and the structure of the cell membrane. It is influenced by ions flowing in and out of channels that open and close with remarkable precision. Everything about this process can be measured with electrodes, observed in tissue samples and reproduced in simulations. It does not need quantum superposition to happen. It is simply biology doing its job. When the electrical impulse reaches the end of the axon, the neuron communicates with the next cell through a chemical messenger known as a neurotransmitter. The axon terminal releases these molecules into a tiny gap called the synapse, where they drift across and bind to receptors on the receiving neuron. This triggers new electrical changes which may activate that neuron or quiet it down. thought, memory, movement, emotion. They all arise from these countless interactions happening every moment. Once again, the behavior of neurotransmitters follows classical chemistry. Molecules diffuse, receptors change their shape, ions flow, and signals continue on their way. The brain contains trillions of these synaptic connections, forming networks so intricate that even the most powerful computers struggle to model them. Yet despite this complexity, the underlying physics remains classical. The ingredients behave in predictable ways. Electrical signals propagate with consistent speeds. Chemical messengers follow known pathways. If you apply a certain drug, the resulting change in neural activity can be measured with remarkable accuracy. If a particular region of the brain is stimulated, the associated behavior often becomes clear. Neural networks respond to patterns, form memories, strengthen connections, and weaken others, all through processes grounded in classical biology and chemistry. This classical framework is how neuroscience explains most aspects of thought and awareness. You can look at activity in the visual cortex and see how the brain processes images. You can observe patterns in the auditory system and see how the brain interprets sound. You can record signals from deeper regions and watch how emotions form. Even complex processes like attention and decision-making can be traced through the ebb and flow of neural activity. All of this fits comfortably within the rules of everyday physics. Nothing about these explanations requires quantum entanglement or quantum coherence. They require cells that fire, chemicals that travel, and circuits that adapt. A gentle way to picture this is to imagine the brain as a vast city at night. Neurons are like homes and buildings glowing with light. Electrical impulses act like the flow of power across the city grid. Neurotransmitters are like messages carried through roads and alleyways. Some areas bustle with activity, while others remain quiet. Patterns of light shift as thoughts move, memories form, or emotions rise. The city is enormous and full of life, but every part of it obeys ordinary rules. There is nothing in this picture that needs the unusual behaviors found in the quantum realm. The city shines brightly because of classical, reliable processes working in harmony. This classical view also explains why the brain is not usually seen as a quantum device. Quantum effects are delicate. They flourish in cold, isolated environments where interactions are carefully controlled. The brain, by contrast, is warm, constantly active, and full of molecular activity. Ions rush through channels. Proteins fold and unfold. Electrical impulses fire rapidly. Molecules bump into one another without pause. All of this noise tends to wash away quantum coherence almost instantly. In a sense, the brain is too lively and too warm to preserve the fragile states that quantum processes rely on. This does not mean the brain ignores quantum physics entirely. At the smallest scales, every atom and particle still behaves according to quantum rules, but once those atoms assemble into large structures and interact vigorously with their surroundings, their behavior averages out into classical patterns. A neuron is made of quantum particles, but a neuron does not behave like a quantum particle. A synapse is built from molecules that follow quantum rules, but the way neurotransmitters cross the synaptic gap can be described perfectly well with classical chemistry. This is why classical physics is the default for understanding the brain. It works. It is reliable. It explains the vast majority of what neurons do. The strength of classical neuroscience becomes even clearer when you consider how much of the brain has been successfully mapped using these principles. Scientists can track how signals move across the cortex. They can measure patterns that predict movement, emotion, and perception. They can use brain imaging to observe regions that activate during certain tasks. They can study how networks reorganize themselves after injury, how learning strengthens connections, how memory relies on changes in synaptic strength. None of these discoveries required new physics. They relied on careful observation, detailed models, and the interconnected framework of classical biology. Yet there is also a gentle humility in this classical approach. It explains how the brain processes information, but it does not fully explain why any of this processing feels like something from within. Classical physics can describe the movement of ions and the firing of neurons, but it does not answer the deeper questions about subjective experience. The classical view is not wrong. It is simply incomplete. It provides the mechanisms, but not the inner feeling. This is one reason some researchers have wondered whether something more may be involved, whether the mind might draw upon processes beyond classical explanation. Still, before wandering into those possibilities, it is important to reaffirm that classical neuroscience is exceptionally successful. Most of what the brain does can be understood through the behavior of cells and chemicals working in vast networks. The brain does not need quantum strangeness to form thoughts. It needs stable electrical pulses, reliable chemical messengers, and richly interconnected pathways that have evolved over millions of years. A bit of light humour may help here. If neurons could speak, they might politely suggest that they have quite enough work on their plates, without adding quantum responsibilities. They already fire hundreds of times per second, maintain delicate ion balances, repair their own structures, and communicate across enormous networks. Asking them to also manage quantum superpositions might feel like assigning calculus homework to someone already struggling with a full-time job. This chapter serves as a quiet reminder that classical physics provides a sturdy foundation for understanding the brain. It explains how signals move, how information flows, and how networks create patterns that shape thought and behavior. It shows a system that is active, adaptive, and exquisitely complex, yet still grounded in familiar rules. Only after appreciating this classical landscape can the mind gently wonder whether something deeper might lurk beneath it, waiting for attention. The question of whether the brain can host quantum effects begins with a simple but important observation. The brain is warm, wet, and constantly in motion. It is a biological environment filled with jostling molecules, electrical pulses, flowing ions, and ceaseless chemical reactions. Quantum effects, on the other hand, are famously delicate. They thrive in places that are cold, quiet, and shielded from disturbance. Laboratories often go to extraordinary lengths to create such conditions. They cool materials to near absolute zero, isolate them from vibration, and protect them from even the faintest sources of noise. Only then do quantum states linger long enough to measure. So how could such fragile behavior survive inside the brain, a place that resembles a bustling marketplace more than a peaceful temple? This is the central difficulty in imagining quantum consciousness. It is not about whether quantum physics exists in the brain. It certainly does. Every atom, every electron, every molecule behaves according to quantum rules. The question is whether the brain can sustain the special kinds of quantum states that might meaningfully contribute to awareness. These states require coherence, a gentle form of synchronization that allows particles to act in unified, delicate patterns. Coherence is easily lost, washed away by interactions with the environment. A calm way to imagine coherence is to picture a group of fireflies blinking in perfect rhythm. They shine together, forming a coordinated glow. Decoherence is what happens when a breeze blows through the meadow, stirring the branches and scattering the fireflies. They continue to blink, but not in time. Their synchrony fades. In the quantum world, decoherence happens when a particle interacts with its surroundings. Even a single bump from a passing molecule can disrupt a fragile quantum state. In a warm environment, such bumps happen constantly. This is why many scientists doubt that quantum coherence can survive in the brain for more than unimaginably short moments. Neurons fire rapidly, Molecules vibrate with energy. Water molecules collide billions of times per second. The temperature is high relative to quantum scales, and the structure is anything but still. Decoherence would wash away quantum states almost instantly, leaving no time for them to influence thought or awareness. At least that is the classical view. But not everyone agrees. Some researchers argue that certain structures inside neurons, particularly within the cytoskeleton, might provide tiny pockets of stability. They suggest that these structures could shelter quantum processes from the surrounding noise. The idea is not that the entire brain becomes a giant quantum computer, but that specific regions or molecules might maintain coherence long enough to matter. This remains controversial, not because the idea is outrageous, but because it is difficult to test. Quantum states are hard to measure under controlled laboratory conditions, let alone inside living tissue. The experimental tools required are delicate, precise, and often incompatible with the complexity of biological systems. Even detecting quantum behavior in a single protein is a monumental challenge. Doing so in the dynamic environment of the brain pushes technology to its limits. This is why the debate continues. It's not a question of belief, but of evidence. And evidence in this case is incredibly hard to obtain. Some experiments in quantum biology have offered gentle hints that quantum effects may survive longer than expected in certain systems. Photosynthesis, for example, appears to rely on quantum coherence to help plants transport energy efficiently. Certain birds seem to use quantum processes in their magnetic sensing. These discoveries remind scientists that nature sometimes shelters quantum behavior in surprising places. If a leaf can harness coherent states at room temperature, perhaps a neuron could as well. But these hints are far from proof, and they come with their own complexities. A soft metaphor may help here. Imagine trying to hear a single whisper during a lively street parade. The whisper represents a quantum state. The parade represents the biological environment. Most of the time, the whisper is drowned out. But occasionally, if the buildings align just right and the breeze settles, the whisper might echo between the walls just long enough to be heard. Some researchers believe that the brain might contain such architectural alignments, tiny pockets where the whisper of quantum behavior could slip through the noise. Others believe the parade is simply too loud, and that no such whispers survive long enough to matter. The brain operates on timescales far slower than quantum events. A neuron firing might take a few thousandths of a second. A synaptic transmission might last a few millionths. But quantum states can collapse in unimaginably tiny fractions of a second. This mismatch makes it difficult to see how quantum processes could shape neural behavior. If coherence fades too quickly, it has no chance to influence the larger system. This is one of the strongest arguments against the plausibility of quantum consciousness. Yet the brain is not merely a chaotic collection of molecules. It is an exquisitely organized organ with structures that repeat, stabilize, and coordinate. Microtubules, cytoskeletal filaments, lipid membranes, clustered proteins. Some theories suggest these might support quantum effects by reducing environmental noise. Imagine them as tiny, quiet rooms inside a bustling building. Whether these rooms actually exist in the way theorists imagine is still unknown, but the idea continues to inspire research. Scientific debate rarely settles gently. It often sways like a tree in the wind, with branches reaching in different directions. Some physicists argue that quantum effects are too fragile for the brain's conditions. Some neuroscientists argue that classical explanations are sufficient and have already explained much of cognition. Others, bridging both worlds, argue that the brain structure may not be as hostile to quantum behavior as once believed. They see the possibility of stability emerging from the brain's geometry, rather than despite it. It is important to approach this question without taking sides too quickly. The idea of quantum consciousness is not supported by conclusive evidence, but neither is it ruled out with certainty. it sits in a space where curiosity is both reasonable and necessary. The difficulty lies not in the concept itself, but in the challenge of measuring something so delicate in an environment so lively. Another gentle metaphor can help capture the essence of the problem. Imagine trying to draw a pattern on the surface of a pond during a rainstorm. Each raindrop disrupts the pattern before it fully forms. Coherent quantum states are like those patterns. The brain, with its constant chemical and electrical activity, is like the pond in the rain. For a coherent pattern to last long enough to matter, something in the system would need to shelter it from the downpour. This chapter serves as a quiet reminder that merging quantum physics with brain function is not straightforward. The brain's warmth and activity challenge coherence. Yet nature has surprised us before with quantum resilience in unexpected places. The debate continues not because the idea is fantastical, but because the tools required to confirm or deny it remain limited. Quantum consciousness sits at the edge of possibility, not confirmed, not dismissed, but hovering in a space where science has not yet looked deeply enough. Whether the brain can sustain quantum states long enough to influence awareness is a question that cannot be answered by intuition alone. It requires careful thought, new instruments, and a willingness to let the mystery unfold in its own time. For now, the idea remains as fragile as the quantum states it seeks to describe, shimmering at the boundary between what we know and what we hope to understand. One of the most widely discussed ideas linking quantum physics to consciousness is the Orch OR proposal, developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. The name sounds complicated, but at its heart the idea tries to solve a simple and profound question. How does the brain produce the rich, unified experience of being aware? Penrose and Hameroff believed that classical physics alone could not account for this. They suggested that consciousness may arise from quantum processes happening inside tiny structural components of neurons called microtubules. The theory is bold, controversial, and imaginative, which is partly why it continues to attract curiosity. Understanding it gently requires stepping into both neuroscience and quantum physics, and then drifting quietly into a place where the two might meet. Microtubules are long, cylindrical structures found inside almost every cell in the body, including neurons. They help maintain the cell's shape, provide tracks for transporting molecules, and support many internal processes. You can picture them as the internal scaffolding of the cell, forming a delicate, dynamic lattice. Hameroff believed these microtubules were not just structural components. He proposed that they might be capable of supporting quantum states, acting almost like tiny circuits capable of coherent behavior. Instead of neurons being the smallest meaningful units in brain computation, he suggested that microtubules might play a deeper, more fundamental role. Penrose, meanwhile, approached the problem from the direction of physics and mathematics. He argued that consciousness could not be explained solely through conventional computation. In his view, something non-algorithmic was needed, something that could not be captured by classical information processing. He believed that certain kinds of quantum processes might provide this missing ingredient. Specifically, he proposed a mechanism called objective reduction, a theoretical process where quantum states collapse, not because of external measurement, but because of limits built into the structure of space and time itself. When these collapses occur, Penrose suggested, they create occasions of conscious experience. The Orch OR theory combines these two lines of thinking. In simple terms, it proposes that microtubules inside neurons can sustain quantum states long enough for objective reduction to take place. These reduction events, occurring across networks of microtubules, would then give rise to moments of conscious awareness. The brain would not merely be processing information through synapses and firing patterns. It would be participating in a deeper, more fundamental layer of reality where quantum processes help shape thought. A soft metaphor may help clarify the intuition behind the idea. Imagine the brain as an orchestra. Classical neuroscience describes the musicians, their instruments, and the sheet music guiding their performance. Orch OR suggests that beneath this orchestral layer lies another, quieter layer. A layer where the very air in the concert hall vibrates with delicate harmonies that subtly influence the music. The proposal is that consciousness does not come only from the musicians playing, but also from these deeper harmonics shaping the experience. The idea is intriguing, but it faces significant challenges. The first is the problem of decoherence. Quantum states are fragile, especially in warm, active environments like the brain. Critics argue that microtubules are unlikely to protect quantum states long enough for objective reduction to occur. Decoherence, they say, would wash away coherence much too quickly. Supporters counter that microtubules may have special structural features that shelter quantum behavior. Some point to patterns within microtubules that resemble ordered crystals, which can sometimes support quantum effects. Others suggest that biological systems may be more adept at maintaining coherence than previously believed. Another criticism concerns the plausibility of objective reduction itself. Penrose's idea is bold, but it remains theoretical. It suggests that quantum state collapse is tied to the very fabric of space-time. Some physicists find this appealing, while others argue that the concept remains unproven and difficult to test. The theory stretches beyond established quantum mechanics into speculative territory. Critics note that even if objective reduction is real, there is not yet clear evidence that it plays a role in consciousness. There are also questions about scale. Conscious experience emerges from networks of neurons involving massive amounts of information. Could quantum processes inside microtubules meaningfully influence such large-scale phenomena? Some argue that even if microtubules can host quantum states, it is unclear how these states would shape the behavior of entire neural networks. Others believe that small quantum influences could cascade upward, affecting neuron firing patterns in subtle but meaningful ways. Still, despite these criticisms, the Orch OR proposal continues to inspire research. Part of its appeal is that it attempts to address the mystery of subjective experience directly, rather than simply describing neural mechanisms. It acknowledges that consciousness feels different from other physical processes and asks whether something fundamental might be missing from conventional explanations. Even scientists who disagree with the theory often appreciate that it pushes the boundaries of the conversation. Recent research has brought renewed interest to microtubules themselves, even outside the quantum debate. Their structure is remarkably dynamic. They assemble and disassemble rapidly. They help organize the internal components of the neuron. They may even influence how signals travel from one part of the cell to another. Whether or not they host quantum states, microtubules clearly play important roles in cellular function. Some studies have hinted at unusual vibrational properties within microtubules, which has encouraged researchers to explore whether their structure might allow for quantum behavior under certain conditions. These findings are preliminary and far from conclusive, but they keep the topic alive. A gentle way to hold the Orch OR proposal is to see it as a bridge between worlds. It stretches from the mechanical landscape of the cell to the shimmering possibilities of the quantum realm. It offers a story about consciousness that is both scientific and poetic, suggesting that awareness might arise from the geometry of space and time filtered through the delicate structure of microtubules. Whether this picture is accurate remains unknown, but it opens a space for curiosity. It is also important to acknowledge that scientists who critique Orch OR are not dismissing the mystery of consciousness. They simply believe that classical explanations go far enough, or that quantum processes inside the brain are unlikely to survive long enough to matter. Their caution is grounded in evidence. Their skepticism reflects scientific discipline rather than disregard for the mystery. At the same time, theories like Orch OR remind the scientific community to explore gently at the edges of knowledge. The brain is an extraordinarily complex organ, and quantum physics is an extraordinarily rich theory. Bringing them together is challenging, but challenges are often where interesting discoveries begin. In the end, the Orch OR proposal remains one of the most famous attempts to link quantum physics with consciousness. It is imaginative, controversial and courageous. It has inspired research, debate, and new lines of questioning. Whether it turns out to be correct or not, it has encouraged scientists to examine both the smaller scales of reality and the deepest layers of the mind, and that alone gives it a place in the story of how we try to understand awareness. Quantum biology is one of those fields that sounds almost contradictory at first. Biology brings to mind warm, living systems full of motion and complexity, while quantum physics evokes images of tiny particles behaving in delicate and improbable ways. Yet over the last few decades, scientists have discovered that certain forms of life appear to take advantage of quantum tricks, using them with a precision that feels almost poetic. These discoveries do not prove that the brain uses quantum processes to generate consciousness, but they do show that quantum behavior can survive in biological environments, sometimes in surprising and elegant ways. This has encouraged some researchers to wonder whether the brain might also harbour pockets of quantum activity, even if only in certain specialised structures. One of the most striking examples of quantum behaviour in life lies within photosynthesis. Plants, algae, and certain bacteria rely on the efficient transfer of energy from sunlight to begin the process of turning light into fuel. At the microscopic level, this involves moving energy across a network of molecules inside specialised structures. For many years, scientists assumed this energy hopped from one molecule to the next in a classical step-by-step fashion. But experiments revealed something different. The energy appeared to explore multiple pathways at the same time, as though it drifted through a shimmering landscape of possibilities and then settled on the most efficient route. This behaviour resembles quantum superposition. Rather than randomly guessing a pathway, the system seemed to test several at once, choosing the best one in a fraction of a second. A calming way to visualize this is to imagine a traveller standing at the edge of a forest filled with winding trails. In the classical world, the traveller would test one path at a time, wandering down each to see which leads to the destination. In the quantum-inspired view, the traveller somehow samples all the trails simultaneously, sensing the entire forest in a single moment and then stepping confidently onto the most efficient route. The result is astonishingly fast and efficient energy transfer. This discovery does not mean the plants are consciously examining possibilities. It simply reveals that nature occasionally uses quantum effects as part of its design. Another beautiful example comes from the world of birds, particularly migratory species like robins. For many years, scientists puzzled over how birds navigate thousands of miles with such accuracy. One emerging explanation involves a quantum mechanism inside specialized proteins in the bird's eye. These proteins, called cryptochromes, may allow birds to sense the Earth's magnetic field through a quantum process involving pairs of electrons. When light hits the proteins, it may create electron pairs whose quantum states depend on the direction of the magnetic field. This could provide birds with a sense of orientation, a kind of internal compass that relies on quantum entanglement. A gentle metaphor here might be to imagine a bird gliding through the air with a tiny, silent map woven into each wingbeat. The map is not ink on paper, but a shifting quantum whisper that guides the bird across vast distances. The bird does not think about entanglement or electron spins, it simply follows the quiet sense of direction nature has built into its body. Quantum effects have also been proposed in the sense of smell. The classical explanation for smell is that molecules bind to receptors in the nose, like keys fitting into locks. But some scents behave in ways that do not fit neatly into this model. A quantum hypothesis suggests that smell might rely not only on the shape of a molecule, but also on how electrons vibrate within it. These vibrations could be detected by receptors through a quantum process known as tunneling, where electrons move in ways forbidden by classical rules. This idea remains debated, but it opens the imagination to the possibility that even something as everyday as sniffing a flower could involve quantum subtleties. What these examples show is that quantum mechanics is not confined to cold laboratories and isolated experiments. Life itself sometimes uses quantum strategies to solve problems, and it does so within warm, noisy environments. This alone does not prove that the brain uses quantum mechanics to generate consciousness, but it does soften the skepticism. If plants can use superposition, if birds can use entanglement, and if molecules in the nose might use quantum tunneling, then perhaps biological systems can be more quantum-friendly than once believed. Still, it is important to draw a gentle boundary between what is known and what is speculative. The quantum effects in photosynthesis are supported by strong experimental evidence. The bird navigation mechanism is supported by compelling data, though some details remain unresolved. The quantum theory of smell is more controversial and still under investigation. These examples show that quantum biology is a real and growing field, but they do not imply that every biological process has a quantum explanation. This distinction matters, especially when thinking about the brain. Quantum biology demonstrates that nature can maintain delicate quantum states under certain conditions. It reveals that biological structures sometimes act as surprising guardians of coherence, allowing patterns of possibility to linger longer than expected. But it does not automatically follow that neurons or microtubules behave in the same way. The brain is incredibly complex, and its machinery is different from the systems that support quantum effects in photosynthesis or magnetoreception. The existence of quantum biology does not guarantee quantum consciousness. It simply shows that the idea is not impossible. A soft way to think about quantum biology is to imagine nature as an artist working at two scales. At the large scale, nature paints with bold strokes using classical physics. At the smaller scale, she uses fine, shimmering detail, touching molecules with quantum precision. In some places, those small-scale touches allow for extraordinary abilities, like guiding birds across continents or harvesting sunlight with near-perfect efficiency. Whether the brain also uses this fine brush remains an open question. These discoveries encourage scientists to look more closely at structures within neurons, such as microtubules, molecular clusters, and protein complexes. If quantum effects appear in photosynthetic systems, which are also warm and dynamic, could similar structures exist in the brain? If birds can sustain entangled states long enough to navigate vast distances, could a neuron support coherence long enough to contribute to information processing? These questions are part of what keeps the study of quantum consciousness alive, not as a claim, but as a possibility worth exploring gently. Importantly, quantum biology also teaches patience. These quantum tricks were hidden in plain sight for decades before being discovered. They required new tools, new theories, and new ways of analyzing biological systems. The brain is far more complex than a photosynthetic molecule or a protein in a bird's eye. If quantum effects play any role in its function, the signals may be subtle, fleeting, or woven into patterns we have not yet learned to detect. In the end, quantum biology offers a soft reassurance. It shows that nature is not afraid to dip into the quantum world when it is useful. It reveals that the boundary between classical and quantum behavior is more flexible than once believed. And it reminds us that the universe often hides its most delicate tricks in the smallest corners of life. Whether those tricks appear in consciousness remains unknown, but the fact that they appear at all keeps the question alive, shimmering quietly at the edge of what we understand. Entanglement is one of the most delicate and surprising behaviours in the quantum world, and it is often the first idea people turn to when they wonder how quantum physics might relate to consciousness. At its heart, entanglement is a kind of interconnectedness. When two particles become entangled, their states link in a way that remains meaningful no matter how far apart they travel. What happens to one tells you something about the other instantly, as though they share a quiet understanding beneath the noise of the universe. Physicists do not interpret this as communication, nor as anything mystical. It is simply the way quantum reality operates when particles share a deep mathematical relationship. But even with this grounded explanation, the image of such a link can feel almost poetic. A soft way to picture entanglement is to imagine two leaves drifting on the surface of a calm lake. Even if a breeze sends them in different directions, they somehow continue to curl in the same rhythm, as though remembering the moment they touched. Their motions are not controlled by each other, yet they echo one another in a subtle, persistent way. Or imagine two dancers beginning on the same stage, taking different paths, yet subtly mirroring one another's movements long after they part. These metaphors are imperfect, but they capture the sense of connection that entanglement suggests. Because of this sense of connection, some researchers and philosophers have wondered whether entanglement might play a role in consciousness. One of the great puzzles of awareness is that it feels unified. You do not experience vision and hearing as separate, independent streams. You do not feel your thoughts in one corner of your mind and your emotions in another. Instead, everything blends into a single, seamless moment of being. This unity is remarkable, especially considering how divided the brain's processing truly is. Different regions handle sight, sound, touch, memory, and decision-making. Yet the result feels like one continuous experience. This has led to speculative ideas that perhaps consciousness arises from some form of quantum interconnectedness. If entanglement allows distant particles to share states in a coordinated way, some have asked whether similar mechanisms inside the brain might allow different regions to share information more directly than classical physics would normally permit. The idea is not that neurons are entangled in the dramatic physics textbook sense. Rather, some theorists imagine that microscopic structures or processes might become subtly linked, helping create the unity that consciousness displays. A gentle metaphor brings this idea to life. Picture consciousness as a vast tapestry woven from many threads. Each thread represents a piece of sensory information, a memory, a thought, an emotion. Even though the threads come from different parts of the loom, the final tapestry feels whole. Entanglement in speculative theories acts like a hidden weaving technique, binding threads together beneath the surface. It does not create the tapestry, but it helps hold its patterns in place. Philosophers find entanglement particularly fascinating because it challenges familiar assumptions about separateness. In classical physics, objects are distinct. They have their own properties, their own boundaries. Entanglement blurs this distinction. Two entangled particles do not have fully independent identities. Their properties exist in relation to each other, even when separated by great distance. This has sparked philosophical reflections on the nature of connection, the meaning of individuality, and whether the universe is more deeply interwoven than it appears. When philosophers turn this lens toward consciousness, they sometimes imagine that the unity of subjective experience might reflect a kind of deep coordination, an underlying connectedness among processes in the brain. If entanglement shows that the universe can link particles in surprising ways, perhaps consciousness is another expression of how the universe weaves relations into the fabric of reality. These ideas are gentle, imaginative, and often poetic, They do not claim that entanglement explains consciousness. They simply wonder whether the hints of interconnectedness found in physics might resonate with the interconnectedness felt in the mind. However, it is important to approach these ideas with scientific caution. Although entanglement is real and measurable, there is currently no evidence that large biological systems, especially warm and active ones like the brain, sustain entanglement long enough to influence neural processes. Entanglement in the laboratory requires extreme care. Systems must be cooled, isolated, and protected from environmental noise. The brain, by contrast, is full of constant activity. Molecules collide, electrical potentials change, and proteins shift. These conditions tend to break entanglement almost instantly. Critics of quantum consciousness often point out that entanglement collapses extremely quickly in biological environments. Any entangled states that might form within the brain would decohere before they could influence neuron-level processes. This makes it difficult to imagine entanglement playing a meaningful role in awareness. It is not impossible, but it is highly challenging under known conditions. These arguments are grounded in physics and deserve careful consideration. Supporters of the idea respond that nature can sometimes shelter quantum behavior in surprising ways. Birds appear to use quantum entanglement in their magnetoreception. Photosynthetic systems use coherence to transfer energy efficiently. These are narrow, specialized situations, but they show that biological environments are not always hostile to quantum effects. Some theorists propose that the brain may contain nanoscale structures capable of shielding entanglement or sustaining it long enough to matter, even if only for short periods. Others suggest that even tiny, fleeting quantum events could influence neural activity in subtle ways. These possibilities remain speculative, but they are explored with curiosity rather than certainty. A gentle reminder can help keep the conversation grounded. Entanglement is astonishing, but it is also precise and limited. It does not bind entire macroscopic systems into unified wholes. It does not transmit thoughts or feelings. It does not create shortcuts through space or time. Instead, it links specific properties of particles in specific ways. Whatever role it might play in consciousness would have to respect these limits. Scientific caution ensures that imagination does not drift too far from evidence. Still, the fascination remains. Entanglement hints that the universe contains forms of connection that defy everyday intuition. It suggests that separateness is not always as absolute as it seems. For a field like consciousness research, which wrestles with the mystery of unity and the interconnectedness of experience, this resonance can be powerful. Even if entanglement turns out to have no role in awareness, it invites a way of thinking about consciousness that feels soft, expansive, and reflective. Perhaps the deepest connection between entanglement and the mind is metaphorical rather than mechanical. Both remind us that the world is not simply a collection of isolated pieces. Both reveal that relations matter as much as parts. Both suggest that wholeness can arise from intricate patterns of interaction. And both encourage a gentle curiosity about how the smallest scales of reality and the brightest moments of awareness might reflect one another. Entanglement offers more wonder than explanation. It provides a beautiful example of how connected the universe can be, even in its quietest depths. Whether the mind uses such interconnectedness directly remains unknown. But thinking about it opens a space for reflection, a place where science and philosophy can share a quiet conversation about the nature of unity, experience, and the delicate links that weave reality together. Superposition is one of the gentlest, yet most mind-bending ideas in quantum physics. It describes a situation where a tiny particle does not occupy one definite state, but instead exists in a cloud of possibilities. Before it is measured or disturbed, it is not here or there, not this or that, but a soft blend of potential outcomes. To someone new to quantum physics, this sounds almost poetic, like a particle drifting through a dream where many futures coexist at once. And in a way, that gentle image is not far from the truth. Superposition is the mathematics of possibility woven directly into the fabric of nature. A calming way to picture superposition is to imagine a small boat floating on a perfectly still lake at dawn. There is no wind, no ripple, no disturbance. In this stillness, the boat does not commit to any single direction. Instead, it drifts in a quiet readiness, able to point north, south, east, or west, but not locked into any one of them. Only when a breeze arrives does the boat decide its true heading. Superposition is this moment before the breeze, the moment where the future is wide open and all directions remain softly available. In the quantum world, superposition means that a particle can occupy multiple potential states until a measurement nudges it into one. It is not literally in many places at the same time in a physical sense. Instead, it carries a collection of possibilities, all woven into its description. When something interacts with the particle, these possibilities condense into a single outcome. The moment of measurement is like the moment the breeze finally nudges the boat. Now, although the mind is not a quantum particle, many people find the concept of superposition appealing when thinking about thought itself. The human mind is remarkably good at holding multiple possibilities at once. When you consider a decision, you can imagine different futures. When you think about a problem, you can entertain several solutions. When you reflect on feelings, you can hold conflicting emotions together without one completely pushing out the other. Thought is not linear, it is not always tidy. Sometimes it feels as though the mind rests in its own gentle superposition, exploring many directions before choosing one. This resemblance is metaphorical rather than literal, but it is a soothing way to understand cognitive flexibility. When you imagine two choices, you are not physically occupying a quantum state. Your neurons are not drifting through a haze of uncertainty. But your mind can entertain possibilities without immediately collapsing them. It can sit with ambiguity, weigh alternatives, and allow ideas to coexist. This is one of the quiet strengths of consciousness. It can hover at the edge of a decision, exploring multiple imagined worlds before committing to one. A soft example might be the experience of standing in front of a branching path on a morning walk. Before you choose, both paths exist in your awareness. You can picture the sunlight filtering through the trees on the left, or the open field spreading out to the right. You're not yet walking down either path, but both feel present. Both have meaning. Both belong to your mental landscape. Only when you begin to move does one become real. The other fades. But the moment of possibility felt real too in its own quiet way. Scientists have sometimes explored whether this ability of the mind to hold multiple ideas might reflect deeper computational strategies, but they do not mean superposition in the quantum sense. Classical neural networks, for example, can represent incomplete or blended states of information. Thought is not simply an on-off switch. It often includes shades, gradients, and mixtures. This richness allows the mind to navigate uncertainty, creativity, and imagination. In a metaphorical sense, the mind can explore many futures at once, even if it does so using biological processes grounded in classical physics. However, it is important to gently clarify that the mind's flexibility does not imply that it relies on quantum superposition in the physical sense. When a neuron fires or a synapse releases a chemical messenger, these events follow biological rules, not quantum probability waves. The comparison between superposition and thought is poetic, not mechanical. It helps describe the feel of mental exploration, but it does not claim that thoughts literally exist as overlapping quantum states. Still, the metaphor resonates deeply because human thought often behaves in a way that feels spacious. Creativity thrives when ideas mix and overlap. Imagination grows when boundaries soften. Problem solving becomes easier when multiple perspectives can sit together without conflict. Many of the most human experiences, wonder, curiosity, hope, depend on the ability to hold open a space of possibility. In this sense, superposition serves as a gentle mirror, reflecting how the mind approaches the unknown. One of the reasons superposition captivates philosophers is that it challenges the idea of definite reality. If the building blocks of matter exist as possibilities before becoming actualized, then perhaps the world is not as fixed as it appears. This raises questions about free will, perception, and the role of the observer. While none of this directly translates into consciousness, it offers imaginative parallels. The mind, like a particle in superposition, often rests in a place where many potential experiences or actions feel equally real until one rises to the surface. Cognitive flexibility, the ability to shift between thoughts or adjust to new information, is another area where people sometimes draw inspiration from quantum ideas. The brain can reconfigure itself, learn quickly, and adapt to changing conditions. When you encounter something unexpected, your mind can generate a spectrum of possible interpretations almost instantly. It can settle on one, revise it, or drift between them as needed. This adaptability, while entirely classical in mechanism, feels reminiscent of the quantum idea that systems can hold a range of potential outcomes before settling into one. A gentle metaphor for this flexibility is to imagine a flock of birds turning in unison. For a moment, their movement contains many possibilities. They might soar higher, dip lower, or sweep to the side. The air holds several futures. Then, almost seamlessly, the flock chooses a direction. The choice feels sudden, but it emerged from the many subtle possibilities that came before. Thought can feel like this too, gliding between options until clarity forms. The fascination with superposition also arises because it highlights the limits of intuition. Our daily experience teaches us that things have definite positions and states. But at the smallest scales, nature behaves differently. This invites a gentle humility. If matter itself holds possibilities before choosing a path, perhaps the mind's fluidity is not so surprising. Perhaps the ability to entertain multiple thoughts at once is simply another expression of how complex systems navigate uncertainty and information. With all of this, it is essential to maintain scientific clarity. The mind's superposition-like behavior is not evidence of quantum consciousness. It is a metaphor that helps describe how thought unfolds. The mechanisms behind thinking, decision-making, and imagination are grounded in neural circuits, chemical gradients, and electrical patterns. These classical processes are powerful enough to create a landscape of rich, mental possibilities without invoking quantum mechanics directly. Yet the metaphor remains comforting because it honors the mysterious quality of thought. It acknowledges that the mind often feels spacious, capable of holding many ideas in a soft, shimmering way before settling into one. Superposition as an idea gives us a language to appreciate this. It reminds us that uncertainty can be gentle, that possibility can be beautiful, and that the mind's ability to explore multiple futures is part of what makes awareness so rich. In the end, superposition is both a scientific principle and a poetic reminder. In physics, it describes the structure of reality at the smallest scales. In the mind, it echoes the feeling of standing at a crossroads of thought, where many paths quietly unfold before you choose the one you will walk. One of the most famous puzzles in quantum physics is the observer problem, the question of what it really means to make a measurement. At the core of this puzzle lies a simple idea. A quantum system can exist in a cloud of possibilities, a gentle blend of potential states, until something interacts with it. That interaction is called a measurement, and it causes the system to settle into one definite outcome. This settling is often called wave function collapse, and it has inspired decades of reflection, confusion, debate, and the occasional late-night headache for physicists. Explaining it gently, without letting the mystery overwhelm the moment, requires stepping back and looking at what measurement means in quantum physics compared with what measurement means in everyday life. A soothing way to picture wave function collapse is to imagine a book filled with many possible stories. Before you open it, the book holds all of them at once. Every ending, every twist, every possibility. Once you begin reading, the book reveals one specific story. In quantum terms, the unopened book represents a system in superposition, while opening it represents measurement. The moment you read the first line, the cloud of possibilities condenses into a single narrative. But here is the tricky part. In quantum physics, the reader does not need to be a person. The reader can be an atom, a molecule, a beam of light, or any physical interaction that disturbs the system. This is where many misconceptions arise. In popular culture, the observer problem is often described as though consciousness itself forces the collapse, as though the universe waits for a human mind to look at it before deciding what to be. It is a charming idea, and it certainly invites poetic reflection. But this interpretation is not part of mainstream physics. In the laboratory, measurements occur when a system interacts with its environment, not when a person stares at it thoughtfully. A camera that has not yet developed its film can still act as a measuring device. A particle bumping into another particle can serve the same function. Even the ambient heat in the room can collapse a quantum state. The term observer in physics is a source of endless confusion because it suggests a person, when in fact it simply means a physical interaction. The observer is anything that interacts strongly enough with the system to extract information from it, thereby disrupting its fragile possibilities. A gentle way to imagine this is to think of the quantum world as a calm pond. A measurement is not someone watching the pond. It is a pebble falling into the water. The ripple of that disturbance breaks the stillness and shapes the outcome. Whether anyone is there to see the ripple does not matter. The interaction itself is the measurement. So why do some thinkers connect consciousness to the observer problem? Partly because the language of quantum physics can sound personal. Words like observation and measurement evoke images of scientists peering through microscopes, or curious minds altering reality simply by looking. In the early days of quantum theory, even great physicists like Niels Bohr and Werner Heisenberg framed their explanations in ways that sometimes blurred the line between physical interaction and conscious awareness. This opened the door to philosophical interpretations that place the observer at the center of the process. Over time, these interpretations evolved into popular claims that the universe depends on conscious beings to take shape. Another reason is that consciousness is mysterious. Quantum mechanics is also mysterious. It can be tempting to imagine that two mysteries might solve each other, but science rarely works that way. Just because two concepts are confusing does not mean they belong to the same category. The mystery of consciousness arises from subjective experience, the feeling of being aware. The mystery of wave function, collapse, arises from the mathematical structure of quantum theory. While they may inspire one another metaphorically, the connection between them is not established by evidence. Mainstream physics takes a grounded approach to measurement. In this view, collapse happens because quantum systems are incredibly sensitive to interaction. A particle in superposition behaves delicately, but the moment it bumps into its surroundings, its possibilities narrow. The environment leaves a trace, a mark, a bit of information. That trace breaks the superposition. This is why experiments must be conducted in controlled, isolated environments to maintain quantum states long enough to study them. In the real world, warm, noisy, filled with stray photons and jostling molecules, superposition collapses almost instantly. This understanding of measurement explains why the world looks classical on everyday scales. When you place a cup on a table, trillions of interactions occur every fraction of a second. The cup is constantly exchanging information with the air, the table, the light in the room, even the heat from your hand. These interactions collapse any quantum possibilities long before they have a chance to grow. The result is a world that appears stable, predictable, and decidedly non-quantum at large scales. This also explains why the observer problem does not require a human mind. If a stray photon from a light bulb strikes a particle in superposition, that photon becomes entangled with the particle. Information flows between them. The system becomes less coherent, and the superposition collapses. No conscious being needs to intervene. The universe handles the entire transaction automatically, long before a human ever observes the result. Still, the philosophical fascination remains. The idea that conscious observation might shape reality touches something deep in human imagination. It suggests a form of participation in the universe's unfolding, a kind of partnership between awareness and existence. It raises questions about the nature of reality, the meaning of the observer, and the relationship between mind and world. Even if these connections are not supported by physics, they inspire reflection, and reflection is part of what makes consciousness so intriguing. It is worth noting that some interpretations of quantum mechanics, such as the many worlds interpretation, avoid wave function collapse altogether. In these views, measurement does not reduce possibilities. Instead, the universe branches into multiple outcomes. Each possibility becomes real in its own branch. These interpretations remove the observer from any special role entirely. Others, like objective collapse theories, propose that wave functions collapse spontaneously, based on physical laws, not observers. These alternatives show that even within physics, there is no universal agreement about the ultimate meaning of measurement. A gentle bit of humour may help soften the tension. If the universe truly needed conscious observers to collapse wave functions, it would have had a very confusing time during the billions of years before life appeared. Supernovae exploding, galaxies swirling, planets forming. The cosmos was quite busy without anyone around to take notes. Fortunately, quantum systems do not wait for coffee-drinking primates to wake up before deciding what to do. The important point is that consciousness is not required for measurement in quantum physics. The collapse of the wave function, however it is interpreted, results from interaction, not awareness. This distinction matters because it prevents quantum mechanics from being misused as an explanation for consciousness itself. If the observer problem is interpreted too loosely, it can lead to misunderstandings that blur the line between science and metaphor. Yet the fascination remains precisely because the language of quantum physics can feel intimate. The idea of possibilities narrowing into reality resonates with human experience. Decisions, perceptions, and moments of clarity often feel like collapses of potential into actuality. It is natural to see reflections of thought within the structure of the physical world, even if those reflections are poetic rather than literal. Ultimately, disentangling measurement from consciousness helps create a clearer foundation for exploring deeper questions. It allows the mind to appreciate the beauty of quantum mechanics without stretching the theory beyond its evidence. It creates space for consciousness to be studied on its own terms, rather than as a byproduct of misinterpreted physics, and it leaves room for wonder, which may be the gentlest link between quantum puzzles and the experience of being aware. In this way, the observer problem becomes not a declaration about consciousness, but a reminder that the universe behaves in subtle and astonishing ways long before any mind arrives to witness it. The idea that consciousness might collapse the wave function is one of the most enduring and widely repeated claims in the landscape of quantum speculation. It is appealing, intuitive in a poetic way, and it offers a sense of partnership between mind and matter. But like many appealing ideas, it becomes more complicated once you look closely. At the centre of this question lies a simple curiosity. When a quantum system sits in a haze of possibilities and then suddenly picks one, does that moment depend on a conscious observer, or does it happen entirely on its own, without any mind involved? The answer depends on which interpretation of quantum mechanics you follow, and on how carefully the idea of observation is defined. Arguments in favour of consciousness collapsing the wave function often begin with the language of early quantum theory. In the 1920s and 1930s, physicists described measurement in ways that sometimes seem to give human observers a special role. They discovered that quantum systems behave differently when measured, and measurement naturally involved people setting up and reading instruments. The idea grew that perhaps consciousness itself forced the system to settle into a definite state. Supporters of this view argue that the very notion of a measurement implies a mind, because measurement requires knowledge, and knowledge requires awareness. They see consciousness as the final step in the chain that brings a quantum possibility into physical reality. Arguments against this idea, however, are grounded in physics itself. In modern quantum mechanics, measurement does not require consciousness, it simply requires interaction. A particle striking a detector counts as measurement. A photon scattering off a molecule counts as measurement. Even a stray vibration, a flicker of heat, or a passing electromagnetic wave can collapse a quantum state. The world is full of interactions, and each one nudges quantum systems into definite outcomes. This means collapse happens constantly, everywhere, long before any conscious mind takes notice. The universe does not wait for human attention before making decisions. It has been collapsing wave functions since long before life emerged. Famous thought experiments often fuel this debate, and perhaps none is more iconic than the imaginary cat placed into a peculiar box by Erwin Schrödinger. In the thought experiment, the cat is linked to a quantum event, such that in the world of possibility, the cat would be both alive and not alive until someone opens the box. Schrödinger never intended this as a literal scenario. It was meant to highlight how absurd quantum superposition becomes when extended to large objects. He wanted to show that the interpretation that relied on conscious observation led to contradictions when applied to everyday life. Despite this, the image of the cat has wandered into popular culture and refuses to leave, often looking a little confused about whether it should be purring or protesting. A gentle humour can help soften the confusion. If Schrödinger's imaginary cat truly depended on consciousness to decide its fate, it might still be waiting for someone to check on it, sitting in the box wondering if it should take a nap or remain alert. The cat, being a practical creature, would probably ask why humans insist on involving it in philosophical experiments when they could simply give it a comfortable blanket and a snack. Another thought experiment often mentioned in this context is Wigner's friend. Physicist Eugene Wigner imagined a situation where his friend performs a quantum measurement inside a closed laboratory, while Wigner remains outside, unaware of the result. Does the wave function collapse when the friend measures the system, or does it remain uncollapsed until Wigner becomes aware of the outcome? the setup highlights how awkward it becomes to assign consciousness a role in collapse. If collapse depends on awareness, then awareness must be assigned to every observer separately. This leads to paradoxes rather than clarity. Experiments, fortunately, are less dramatic than imaginary cats and philosophical friends. Real laboratory studies confirm that collapse occurs through interaction, not awareness. When a quantum system interacts with its environment in any measurable way, it loses coherence. This is the essence of decoherence, a process not dependent on consciousness. Experiments conducted with photons, electrons, atoms, and molecules repeatedly show that quantum possibilities vanish when the environment provides enough disturbance to extract information. Whether or not a human is paying attention at the time does not matter. The collapse has already happened. Some people argue that because conscious observers choose how to measure a system, they influence the outcome indirectly. While it is true that experimenters choose how to set up their apparatus, the system itself responds to the physical configuration, not the experimenter's inner experience. A detector does not need to know who installed it. A particle does not wait politely for someone to gather their thoughts. These interactions unfold according to the physical conditions at hand. This does not mean the debate is entirely settled. Some interpretations of quantum mechanics, such as the relational view or the participatory universe proposed by physicist John Wheeler, leave room for philosophical reflections about observers, though they do not require consciousness in the sense of human awareness. Wheeler's suggestion that the universe might participate in its own unfolding is poetic, but not a claim that minds collapse wave functions. Even interpretations that highlight the role of the observer treat the observer as a physical system capable of interaction, not as a conscious thinker. It's also worth noting that interpretations that do not require collapse sidestep the question completely. The many worlds interpretation suggests that all outcomes occur in different branches of reality, so collapse never happens at all. In this view, consciousness does not collapse wave functions because nothing collapses. Other interpretations propose hidden variables, objective collapse mechanisms, or spontaneous processes that operate independently of observers. These frameworks demonstrate that consciousness is not a necessary component of quantum theory. Still, the idea that consciousness might collapse the wave function lingers because it carries emotional and philosophical appeal. It suggests that awareness has a special place in the universe, that minds play an active role in shaping reality. It resonates with a human feeling of making choices, of influencing events simply by noticing them, of being at the center of experience. Even if physics does not support this idea, the feeling behind it is understandable. A gentle way to distinguish metaphor from mechanism is to remember that consciousness can change the course of events by guiding behavior, not by altering quantum states directly. The choices you make, the attention you give, the observations you focus on, all influence your actions and surroundings at the macroscopic level. This influence is real and meaningful, but it does not depend on quantum collapse. It arises from networks of neurons, patterns of information, and the remarkable ability of the mind to interpret and respond to the world. The scientific caution here is not meant to dismiss wonder, it is meant to protect clarity. Quantum mechanics does not need consciousness to function, and consciousness does not need collapse to exist. They are separate mysteries, each rich in its own way. Linking them requires evidence, not only imagination. And while imagination is a beautiful starting point, evidence is the gentle compass that helps science stay on course. In the end, the question of whether consciousness collapses the wave function remains a philosophical curiosity rather than a scientific conclusion. Physics shows that collapse results from interaction. Consciousness is a higher-level phenomenon that arises from biological processes. The two may inspire each other metaphorically, but they do not currently meet in mechanism. That said, the idea continues to invite reflection, spark conversation, and remind us that both the quantum world and the world of awareness are filled with intrigue. And perhaps that is why Schrödinger's cat remains undecided. Not because consciousness shapes its fate, but because humans, with all our curiosity, cannot resist a puzzle that lets the mind wander through the many possibilities of reality. One calming way to understand the brain is to picture it as an extraordinary information processor, a living system that gathers signals, transforms them, and weaves them into the tapestry of experience. Every moment your senses collect information from the world, the colour of a lamp, the softness of a pillow, the rhythm of your breathing. The brain receives all of this input, integrates it with memories, and produces a smooth, unified sense of awareness. This flow of information is continuous and effortless from the inside, even though the underlying processes involve billions of neurons whispering signals to one another in intricate patterns. Information theory provides a gentle framework for understanding how these signals carry meaning and how the mind might emerge from their structure. Information theory, in its simplest form, is the study of how messages are encoded, transmitted, and decoded. It examines the structure of signals, the patterns they contain, and the limits of how much information can be handled at once. While the theory originally grew from the world of telecommunications, it has become a valuable lens for understanding the brain. Neurons fire in sequences that carry information like phrases in a language. Synapses adjust their strength, shaping how information flows through networks. Different brain regions specialize in different kinds of processing, but they all rely on the movement and transformation of signals. In this sense, the brain is not only a biological organ, but also a vast and dynamic information system. A soft metaphor can make this idea clearer. Imagine the brain as a quiet library at night. The books are neurons, each containing its own tiny piece of information. Librarians wander the halls carrying messages from one shelf to another, comparing notes, organizing ideas, and highlighting connections. The sound of their footsteps, the tapping of pens, the rustle of pages, all of these are like neural signals moving through the brain in patterns that encode meaning. Consciousness, from this perspective, emerges when the entire library becomes active in a coordinated way, drawing from many shelves at once to create a coherent story. Some researchers wonder whether quantum information might play a role in this story. Quantum information is a different kind of information, built not from classical bits that are either on or off, but from quantum bits that can exist in gentle blends of possibility. These quantum bits can hold more potential configurations than classical ones, and they can become entangled with one another in ways that allow for surprising correlations. If the brain were able to use quantum information, it could, in theory, process certain kinds of information more efficiently, or in ways that classical networks cannot easily replicate. However, whether the brain actually uses quantum information remains a question without a clear answer. Quantum information requires maintaining delicate quantum states long enough for them to be useful. This brings us to decoherence, a gentle but unavoidable process in which quantum states lose their coherence due to interactions with their environment. Decoherence happens incredibly quickly in warm, active systems like the brain. It is like trying to keep a soap bubble intact during a rainstorm. The moment the bubble encounters too much disturbance, it collapses. A calming way to picture decoherence is to imagine a chorus humming a single note. As long as all the singers stay perfectly in tune, the sound is smooth and unified. But even a small disturbance, a cough, a missed pitch, a sudden breeze, breaks the harmony. The unity fades instantly. Quantum states rely on a similar harmony, and the brain is full of tiny disturbances. Molecules jostle one another. temperature fluctuates, ions rush across membranes. These conditions make it difficult for quantum coherence to last long enough to contribute meaningfully to information processing. Most neuroscientists therefore believe that the brain relies primarily on classical information processing. Neurons send signals through electrical pulses. These pulses influence other neurons in predictable, measurable ways. Synapses strengthen or weaken based on patterns of activity, shaping learning and memory. Larger networks form rhythms, oscillations, and synchronized waves, all of which help organize attention, perception, and behavior. These processes are powerful, flexible, and fully capable of generating the rich experience of awareness without needing to invoke quantum information. Still, some researchers take an open-minded approach. They note that classical activity and quantum activity are not mutually exclusive. Even if the brain functions primarily through classical mechanisms, there may be tiny pockets where quantum information plays a subtle role. For example, certain proteins or molecular structures could briefly sustain coherence before decoherence sets in. These fleeting quantum events might influence molecular behavior in ways that cascade upward to larger neural patterns. This remains speculative, but it is part of the ongoing exploration into the brain's inner workings. The central point is that consciousness depends on the flow of information, whether classical or quantum. Each sensation you experience is a pattern of information encoded across neural networks. Each thought is a shifting configuration of signals. Each memory is stored as a particular arrangement of synaptic strengths. The brain constantly interprets, compresses, and expands information, turning raw input into meaningful experience. Information theory helps describe these processes by emphasizing how much data the brain can handle, how efficiently it can organize that data, and how it might integrate different sources of information into a single moment of awareness. A gentle metaphor brings this into focus. Imagine a river made from millions of tiny droplets. Each droplet carries a bit of information, like a tiny packet of meaning. As the river flows, the droplets merge, swirl, and reshape themselves. The riverbed, with its curves and bends, influences how the water moves. In the same way, the brain structure influences how information flows. Consciousness is the feeling of drifting along this river, sensing its motion, its depth, its ever-changing patterns. When researchers use information theory to explore consciousness, they often look at how integrated the information is. If information remains isolated in different parts of the brain, awareness becomes fragmented. When information flows freely between regions, awareness becomes unified and vivid. Some theories propose that consciousness arises when a network processes information in a way that cannot be reduced to the sum of its parts. The whole becomes more than the individual signals. This idea is attractive because it aligns with lived experience. Awareness feels whole, not scattered. The connection between information and consciousness does not depend on quantum mechanics. Even if no quantum information is present, information itself remains central to how the brain works. The patterns, the connections, the rhythms, they all shape what it feels like to be present. Whether the brain occasionally dips into quantum processes is a separate question, and one that remains open. But it is not necessary for explaining the basic structure of experience. A touch of humour can help ease the weight of these ideas. If the brain truly relied on quantum bits to think, it might spend half the day trying to stay coherent, muttering to itself about stray molecules interrupting its focus. Fortunately, the brain is perfectly capable of managing information even while juggling the daily chaos of life. From making breakfast to remembering where you left your keys, quantum precision is not required to maintain this flow, though it would make an interesting excuse for misplacing things. Ultimately, understanding the brain as an information processor provides a stable foundation for thinking about consciousness. It shows how signals become sensations, how patterns become thoughts, and how meaning arises from the shifting activity of countless neurons. It bridges the technical world of neuroscience with the intimate world of experience, whether quantum information plays a tiny supporting role or no role at all. The brain's ability to process and integrate information is what allows consciousness to shine. Free will is one of those ideas that feels familiar and mysterious at the same time. Every day you make choices, small ones, like which side of the pillow feels cooler, and large ones, like what path to take in life. These choices feel personal, they feel deliberate, they feel like yours. Yet beneath that feeling rests a long-standing philosophical question. Are these choices truly free, or are they shaped entirely by prior events? And if randomness enters the picture, does that make our choices freer, or simply more unpredictable? Quantum physics introduces a gentle complication. At the smallest scales of reality, certain events are not determined with certainty. They unfold according to probabilities, meaning that no matter how much information you gather, you cannot predict the exact outcome. A particle might take one path or another. A quantum dot might emit a photon sooner or later. An electron might appear on the left or the right of a detector. These events are not unknown because of ignorance. They're unknown because the universe itself leaves room for multiple possibilities. This is quantum randomness, a kind of built-in unpredictability. A soothing way to imagine quantum randomness is to picture a tiny lantern floating in a dark forest. At each fork in the path, the lantern flickers, choosing one direction or another with a soft unpredictability, as though guided by something subtle rather than by a fixed rule. If you could rewind time to that exact moment, the lantern might choose differently, even though everything else is identical. This unpredictability is not chaos. It follows precise probabilities. Yet it is not fixed either. It is a quiet kind of freedom woven into the structure of matter. Some thinkers have wondered whether this quantum randomness might play a role in free will. If the universe is not entirely deterministic, perhaps the brain could make use of quantum unpredictability in its decision-making. Perhaps at certain tipping points, a tiny fluctuation could influence a neuron's behavior, nudging a thought or action in one direction rather than another. This could introduce an element of unpredictability that makes behavior less rigid, less predetermined. But unpredictability is not the same as freedom. If your decisions were driven purely by randomness, you would not feel in control. Choices guided by chance would not feel like your choices. They would feel accidental, like flipping a mental coin. Free will, as most people experience it, feels intentional. It feels shaped by values, memories, desires, and reflection. It feels guided, not random. This creates a gentle tension between quantum unpredictability and the ordinary experience of choosing. If quantum events influence the brain, they might add subtle variability. But they do not guarantee meaningful freedom. Still, the connection between quantum randomness and human decision-making is interesting to contemplate. The brain is a complex system. Neurons communicate through electrochemical signals that can be sensitive to tiny fluctuations. Some researchers argue that a small quantum event could become amplified through the brain's network, shaping behavior in ways that are neither fully deterministic nor purely random. This amplification would not turn quantum randomness into free will, but it might introduce a softness, a flexibility, a touch of unpredictability that gives choices room to unfold. A gentle metaphor may help. Imagine standing at a crossroads on a windy day. You know the destinations of the paths, and you're thinking carefully about which direction to take. Your thoughts and intentions guide you, but the breeze occasionally nudges you, shifting your attention slightly. It does not decide for you. but it influences the texture of your choice. In this way, quantum fluctuations, if they matter at all, might act like faint breezes rather than controlling forces. Others take a different view. They argue that the brain operates at scales far too large and too warm for quantum randomness to play a meaningful role. Classical processes dominate. Neurons fire in patterns that follow known biological rules. Decisions emerge from networks training on experience and feedback, not from microscopic fluctuations. In this view, quantum randomness exists, but it is washed away by decoherence long before it can influence thought. There is also a philosophical concern. If choices depend on quantum randomness, then they are not directed by the self. If they are entirely determined by classical processes, then they may feel predictable. Free will seems to require something between these extremes. Choices that reflect the individual, shaped neither by rigid determinism nor by blind chance. This is why many thinkers conclude that free will may arise from complex information processing rather than from quantum behavior. The brain integrates vast amounts of information, considers options, weighs consequences, and produces actions that reflect the individual as a whole. In this view, freedom is not about escaping causality or embracing randomness. It is about choosing in a way that is consistent with who you are. Still, curiosity remains because the universe leaves room for both structure and unpredictability. Quantum physics suggests that not every event is determined. Neuroscience suggests that the brain's activity is highly sensitive to initial conditions. Philosophers suggest that agency might emerge from patterns that are neither predetermined nor arbitrary. These ideas do not answer the question of free will, but they deepen it. One gentle way to hold this puzzle is to picture consciousness as a river. The river flows according to the shape of its banks, your memories, your experiences, your hopes. But within the river, currents shift, eddies swirl, and droplets move unpredictably. The overall direction is guided, but the details contain subtle variations. Some of those variations might be classical, some might be quantum. None of them alone explain free will, but together they contribute to the dynamic, living process of choosing. A soft bit of humour can lighten the topic. If your decisions truly depended on quantum randomness, you could blame every impulsive snack choice on a mischievous electron. It wasn't me, you might say. A quantum fluctuation made me grab that extra cookie. While amusing, this explanation rarely satisfies the deeper sense of responsibility that accompanies real choices. The philosophical implications go further. If randomness exists at the foundation of reality, then the universe is not a rigid chain of cause and effect. There is room for novelty, for spontaneity, for patterns that surprise even the systems that generate them. Free will might emerge within this elasticity, guided by structure yet open to variation. But this remains a hypothesis, not a conclusion. Ultimately, the relationship between quantum randomness and free will is unresolved. Some believe quantum fluctuations subtly influence behavior. Others believe free will is a higher-level experience unrelated to microscopic unpredictability. Still others think the entire question needs reframing, because consciousness itself may not fit neatly into deterministic or random categories. Curiosity rather than certainty is the gentlest way to approach this topic. Quantum randomness reminds us that the universe contains true unpredictability. Consciousness reminds us that choices feel meaningful. Somewhere between these two lies a landscape worth exploring, not for answers, but for a deeper appreciation of how complex and beautiful decision-making can be. In summary, free will may not need quantum randomness to exist, or perhaps it does, in ways we have yet to understand. Either way, the gentle mystery remains, shimmering quietly at the edge of experience, inviting reflection without demanding resolution. Time, in everyday life, feels like a gentle river flowing in one direction. Moments arrive, drift past, and become memories. You feel the rhythm of your breath, the pace of footsteps, the settling of evening light. Consciousness seems to rest upon this flow, riding it like a leaf on a stream. Yet when you look closely at time through the lens of quantum physics, the river becomes far stranger. Instead of a steady current, time begins to look like something woven from many possibilities, something that may not behave as smoothly as experience suggests. Understanding this gently helps illuminate both the physics of time and the way the mind stitches moments into a continuous story. In quantum theory, time is not always treated as the simple ticking of a universal clock. Instead, it becomes part of the mathematical framework that describes change. A particle in a quantum state evolves according to rules that allow it to drift through possibilities, with no single predetermined timeline until interactions push it into one. Some interpretations of quantum mechanics even suggest that time may emerge from deeper structures, rather than being a fundamental ingredient of reality. Others propose that different branches of possibility, each with their own sense of time, unfold in parallel. These ideas are not fully settled, but they gently remind us that time is not as straightforward as it feels. A calming metaphor helps here. Imagine a loom weaving threads into a tapestry. The threads represent different potential ways the universe could evolve. The loom's motion represents the underlying rules of physics. When you step back, the tapestry looks like a single, coherent picture, just as your experience of time feels unified. But up close, many threads intertwine before settling into a single visible pattern. Quantum time may be something like that, woven from many potential threads, with the final pattern revealed only after interactions shape the outcome. Meanwhile, the brain experiences time in an entirely different way. The brain does not perceive every moment equally. Instead, it gathers sensory information, organizes it, and blends it together into a smooth flow. This blending is astonishingly effective, even though there are delays in neural processing, gaps in perception, and variations in attention. Consciousness presents you with a seamless timeline. You do not notice the tiny pauses and fluctuations. The mind stitches moments together so gracefully that time feels continuous, even though the underlying processes are not perfectly aligned. A gentle example is the way you perceive motion. When you watch someone walk, your eyes gather snapshots of their position. Your brain fills in the gaps between these snapshots, creating a flowing sense of movement. If the brain did not perform this stitching, the world might appear jumpy or fragmented, more like a flickering slideshow than a smooth experience. The brain acts like a skilled editor, blending frames into a coherent film. Memory also plays a role in shaping time. The past is not stored like a perfect recording. It is reconstructed from patterns of neural activity, coloured by emotion and meaning. This reconstruction gives time a sense of depth and continuity. Without memory, each moment would stand alone, disconnected from those before it. Without anticipation, each moment would lack direction. Consciousness relies on both memory and expectation to create a sense of flow, turning isolated events into a meaningful sequence. Quantum physics and neuroscience meet softly at this point. In quantum mechanics, the future is open, filled with possibilities not yet chosen. In the brain, the future is imagined, filled with predictions based on experience. In quantum mechanics, the past is encoded in patterns of probability. In the brain, the past is encoded in patterns of memory. Neither system treats time as a simple chain of fixed events. Both rely on processes that shape how time unfolds or is experienced. One interesting aspect of quantum time is that it seems reversible at the smaller scales. The laws governing electrons and photons do not care whether time runs forward or backward. Their equations look the same either way. Yet the everyday world does have a direction. Eggs do not uncrack. Smoke does not gather back into a candle. Sound does not politely return to a singer's mouth after drifting outward. This directionality, known as the arrow of time, emerges from the tendency of systems to spread out, to grow more disordered. The brain, like the rest of the world, lives in this forward-moving arrow. It uses this directionality to form narratives, to link causes with effects, to feel the steady march from moment to moment. A soft metaphor captures this beautifully. Picture the mind as a lantern carried along a path at dusk. The lantern illuminates a small region ahead, the immediate future, and casts a gentle glow on the ground behind, the remembered past. Everything else remains in shadow. Quantum physics describes the vast unseen wilderness beyond this circle of light, where many potential paths exist. Consciousness describes the illuminated section, where events become part of experience. Some thinkers wonder whether the brain's sense of time might relate to quantum processes, especially given that neural activity unfolds in patterns that sometimes resemble waves or oscillations. These patterns help synchronize different regions of the brain, aligning perception and memory into a shared flow. While these oscillations are classical rather than quantum, they hint at how sensitive the mind is to timing and rhythm. Slight disruptions in timing can influence attention, emotion, and even the perception of reality. Quantum systems also rely on timing. Coherence, the gentle alignment of quantum states, can persist only for limited intervals before decoherence breaks the harmony. These intervals can be unimaginably short, far shorter than anything detectable by consciousness. Yet they illustrate how delicate and intricate the relationship between time and structure can be. The brain's rhythms operate at slower scales, but they too rely on maintaining coherence across networks. Coherence of a classical kind, not quantum, but still essential for awareness. A light bit of humour can soften the complexity. If the brain truly relied on quantum timekeeping, it would probably lose track of appointments within fractions of a second. I know I had something scheduled, it might say, but the timeline branched, and now I'm not entirely sure which version of me was supposed to be there. Fortunately, the brain's own timing mechanisms are robust enough to keep track of everyday life without relying on the subtleties of quantum clocks. In the end, the flow of awareness does not depend on quantum time directly. But quantum physics inspires a sense of wonder about how time might work beneath the surface of experience. It suggests that time may be more flexible, more layered, more intertwined with possibility than our senses reveal. Meanwhile, consciousness takes the raw material of time and smooths it into a gentle narrative, one that feels steady even as the brain constantly updates, edits, and refines each passing moment. Time in consciousness is not a simple reflection of physical time, it is a creation, carefully assembled, lovingly maintained, and deeply connected to the rhythms of thought. Whether or not quantum time influences this creation directly, the parallels between the openness of quantum possibilities and the fluidity of awareness invite reflection. Both time in physics and time in the mind encourage the same gentle insight. The present moment is always a meeting point, a place where past and future blend into experience. The mind stitches the flow together, and the universe provides the threads. The idea that quantum physics might play a role in consciousness is often associated with the Orch OR proposal, but the landscape is broader and still unfolding. Researchers from physics, neuroscience, biology, and philosophy continue to explore whether quantum processes could influence how the mind works, and if so, in what ways. These explorations are gentle, cautious, and filled with open questions. They do not claim that quantum mechanics explains consciousness, but they ask whether certain quantum behaviors might contribute to the brain's complexity in subtle or unexpected ways. Looking beyond Orch OR helps show just how varied these ideas are, and how science continues to probe the boundaries of what we understand about awareness. One alternative approach begins with the idea of quantum coherence in biological systems. Coherence is the delicate alignment of quantum states that allows particles to act in synchrony before decoherence breaks the pattern. Some researchers propose that certain structures in the brain might maintain pockets of coherence long enough to influence neural processing. These structures could include proteins, membranes, or clusters of molecules that exhibit ordered patterns or special geometries. None of this suggests that consciousness itself is a quantum state. Instead, the idea is that quantum coherence might subtly influence the timing or behavior of neural activity in ways that classical explanations have not yet captured. A soft metaphor helps illustrate this idea. Imagine the brain as an orchestra playing a classical symphony. Most of the instruments follow traditional rules, reading notes from a score and responding to the conductor. But here and there, tiny groups of musicians might whisper quiet harmonies that drift beneath the main melody. These harmonies do not replace the symphony, but they add texture. Quantum coherence, in this view, would be like those faint harmonies, subtle contributions woven into the larger classical performance of the brain. Another approach focuses on quantum tunneling, the ability of particles to pass through barriers that classical physics would forbid. Some have suggested that tunneling might influence ion channels in neurons. Ion channels control the flow of charged particles into and out of cells, helping generate electrical signals. These channels are extremely small, and the behavior of particles within them can be sensitive to quantum effects. If tunneling plays a role in how ions move, it could influence how neurons fire. This does not mean neurons rely on quantum mechanics to think, but it means quantum processes could assist or modify classical behavior in certain situations. Quantum tunneling is not speculation in general. It is a well-known phenomenon in chemistry and biology. Enzymes sometimes rely on tunneling to accelerate reactions. This makes the idea intriguing, though still uncertain, when applied to neurons. If an enzyme can use tunneling to function more efficiently, might a neuron use tunneling to regulate its firing patterns? Research continues to explore this gently, without assuming a connection to consciousness directly. A third line of thought involves quantum information theory. While classical neurons transmit information through spikes and chemical messengers, some theorists propose that molecular components might manipulate information in quantum-like ways. This could involve quantum correlations or subtle forms of entanglement within molecular networks. Again, this is not about creating a quantum computer inside the brain. It is about exploring whether small-scale quantum effects could influence the way information flows through biological systems. These ideas remain speculative, but they encourage scientists to study neural processes at deeper and more detailed scales. Another gentle metaphor invites reflection. Picture the brain as an enormous landscape with countless winding streams. Most of the water flows in well-defined channels, the classical pathways of neural firing. But scattered throughout the landscape are tiny springs that bubble up unpredictably. These springs do not define the shape of the land, but they influence it in subtle ways. Quantum processes, if present, might act like those springs, small sources of variation or sensitivity that shape neural patterns over time. Some researchers explore quantum field theories of the brain. These frameworks suggest that the brain might support collective excitations, patterns that spread across networks in ways reminiscent of fields in physics. These excitations could, in theory, interact with quantum processes at small scales. This approach is mathematically complex and not widely accepted, but it demonstrates the breadth of inquiry. Scientists exploring these ideas are not claiming answers. They're investigating possibilities that lie at the edges of current understanding. There are also models proposing that certain molecules, such as the aromatic rings in neurotransmitters, might sustain quantum coherence for short periods. These molecules interact constantly, forming a dynamic network. If coherence lasts even briefly, it could influence chemical reactions or signaling patterns. Researchers studying quantum chemistry in biological environments have found surprising resilience of coherence under certain conditions. This inspires hope that similar mechanisms might exist elsewhere in the body, though the evidence remains limited. Despite these imaginative approaches, there are significant challenges. The brain is warm, active, and full of noise, conditions that typically destroy quantum states quickly. Experimental tools capable of detecting quantum processes inside living tissue are still developing. Measurements at the molecular scale are difficult, especially in moving, complex environments like neurons. Even when quantum effects are detected in biological systems, determining whether they influence consciousness or cognition is much harder. Another challenge is theoretical. Even if quantum processes occur in the brain, it does not automatically follow that they contribute to consciousness. They might influence metabolism, signaling, or molecular structure without affecting awareness directly. Distinguishing between quantum processes that are essential and those that are incidental is a delicate task. Yet despite these challenges, the field continues to grow. New research in quantum biology shows that nature sometimes shelters quantum states in unexpected places. New tools in imaging and spectroscopy allow scientists to observe molecular behavior with unprecedented detail. New collaborations between physicists and neuroscientists help build bridges across disciplines. This creates a gentle optimism, a sense that understanding the role of quantum processes in life is a matter of time, patience, and careful exploration. A touch of light humour softens the weight of speculation. If the brain truly relied on quantum mechanics for thought, it might spend a good part of the day reminding itself not to decohere. "Please stay focused," it might whisper, "and try not to collapse into a probability cloud before lunch." Fortunately, the brain's classical architecture is robust enough to support consciousness even without such worries. Ultimately, exploring quantum consciousness beyond Orch OR reveals a field filled with curiosity rather than certainty. It shows scientists asking thoughtful questions, building careful models, and acknowledging what is not yet known. It invites a sense of wonder rather than conclusion. Quantum mechanics may or may not play a meaningful role in consciousness, but the search itself deepens our understanding of both physics and the mind, and perhaps that is the heart of it. The quantum brain hypothesis, in all its variations, is not a claim that we already understand consciousness. It is an invitation to explore the edge of possibility, to look more closely at the smallest scales of nature, and to consider how subtle processes might shape the richness of awareness. Whether the answers come from quantum physics, classical biology, or something in between, the journey encourages patience, reflection, and a gentle appreciation for the complexity of being alive. Consciousness exists in a universe woven from quantum threads, a universe where particles shimmer through possibilities, where energy dances in discrete steps, and where the deepest structures of reality behave in ways far stranger than everyday life suggests. And yet within this strange and shimmering framework, minds emerge, not in defiance of the universe's rules, but because of them. This raises a gentle question worth exploring with a soft touch. Why does consciousness find a home in a quantum universe? And how does the cosmos allow something as delicate, complex, and intimate as awareness to unfold? A calming way to begin is to imagine the universe as a vast canvas painted with the colours of quantum mechanics. Every atom, every molecule, every star and cell is shaped by quantum behaviour. Quantum rules determine how particles bond to form matter, how energy flows through systems, how elements are created in stars, and how chemistry unfolds in living organisms. Without these rules, the universe would be stillborn. Atoms would not form, elements would not combine, molecules would not emerge, and life would be impossible. In this sense, consciousness does not appear in spite of quantum physics, but in its shadow, nurtured by the laws that shape the entire cosmos. The existence of consciousness suggests that the universe has arranged itself in a way that allows complexity to flourish. Stars forged the elements needed for life. Planets cooled to host oceans. Molecules formed chains capable of copying themselves. Networks of cells learned to sense and respond to their surroundings. Brains evolved that could integrate information, form memories, dream, reflect, and eventually become aware of their own awareness. This unfolding story looks almost like a chain of delicate coincidences, each one dependent on precise balances in the physical laws. Some thinkers consider possibilities like the anthropic principle, the idea that the universe must be structured in a way that allows conscious observers to exist. If it were not, we would not be here to wonder about it. This is not a grand claim about purpose. It does not imply that the universe was designed for consciousness. Instead, it is a gentle reminder that the conditions capable of supporting life and mind are rare and fragile. A universe with slightly different rules might expand too quickly for structure to form, or might never allow atoms to bind, or might collapse too soon for stars to ignite. In such universes, consciousness could not arise to ponder its absence. A calm metaphor brings this to life. Imagine a garden where seeds drift in the wind. Most seeds land in places where they cannot grow, on bare rocks, in deep water, upon frozen ground. But some seeds, by chance, land in rich soil, where sunlight, water, and warmth allow them to flourish. The universe may be something like this garden. Consciousness is not guaranteed, but given the right conditions, it blooms. Another way to explore this idea is to consider how quantum mechanics allows the universe to be both stable and dynamic. Atoms remain intact because electrons occupy quantized energy levels. Molecules form because quantum rules create bonds with specific shapes and strengths. Life depends on the complexity of chemistry, and chemistry depends on quantum behavior. In this way, quantum mechanics sets the stage for life long before the first cell appears. Consciousness, emerging much later, is a distant branch on a quantum-rooted tree. When viewed from this cosmic perspective, awareness feels like a natural extension of the universe's capacity for complexity. Just as stars glow and galaxies spiral, minds arise when matter becomes organized enough to process information, integrate experience, and form inner worlds. Consciousness may not require quantum mechanics to operate directly, but it requires a universe that is structured by quantum rules. Without them, the raw ingredients for mind would not exist. Some physicists and philosophers have speculated that consciousness might tell us something about the nature of the universe. If the cosmos produces observers capable of contemplating it, perhaps this introspection reflects something fundamental about reality. This idea does not claim that consciousness shapes the universe in any physical sense. Instead, it highlights the simple wonder that matter, governed by quantum rules, can eventually become aware. The universe, through consciousness, gains the ability to reflect upon itself. A galaxy cannot contemplate its own spiral arms, but a mind can contemplate the galaxy. It is worth exploring this gently, without rushing to conclusions. Some interpretations of quantum mechanics suggest that the universe unfolds in branches of possibility. Others propose that all moments exist simultaneously. Still others treat time and space as emerging from deeper quantum structures. Within these interpretations, consciousness sits quietly as an observer, part of the universe, shaped by its rules, but not necessarily altering them. The universe does not need awareness to function. But awareness provides a window into the universe that would otherwise remain closed. A soft metaphor helps illustrate this relationship. Imagine standing on a hill at sunrise. The sun rises regardless of whether you watch it. The colours of dawn exist without your attention, yet your presence transforms the moment into an experience. The sunrise does not depend on you, but the meaning of the sunrise does. Consciousness may be similar. The universe unfolds according to its own laws. Awareness does not change the laws, but it gives them a witness. Some thinkers suggest that consciousness might arise in any universe that allows complexity. Others believe that consciousness may be a rare phenomenon, requiring an extremely narrow set of conditions. Still others wonder whether consciousness might be an inevitable outcome of systems that process information. None of these ideas are proven, and all invite further curiosity. What they share is a sense of gentle amazement that a universe built from particles, forces, and probabilities can produce beings capable of love, memory, imagination, and reflection. Even humour can find a place here. If consciousness were to file a formal complaint with the universe, it might say, "You gave me this incredible ability to think, but you also made the universe so vast that it takes me a lifetime just to understand a fraction of it." The universe might reply, "I gave you curiosity for exactly that reason." Consciousness in a quantum universe is a story of emergence. Quantum mechanics shapes atoms. Atoms form molecules. Molecules form cells. Cells form networks. Networks give rise to awareness. The path is long, intricate, and astonishing. Consciousness does not need to be written into the laws of physics to be meaningful. It simply needs the universe to be rich enough, stable enough, and old enough to give it room to grow. Thinking about consciousness at this scale invites a deep sense of calm. It reminds us that awareness is part of a much larger story, one that began long before the first thought flickered into existence, and one that will continue long after the last thought fades. In a universe built on quantum rules, consciousness becomes a quiet reflection of the cosmos itself, a moment of understanding arising from the vast sea of possibility. Quantum consciousness is a topic that invites wonder, imagination, and a sense of possibility. It reaches across physics, neuroscience, philosophy, and even spirituality. But with this broad reach comes a gentle responsibility to understand what quantum ideas can genuinely explain and what they cannot. This chapter is a calm clearing in the forest of speculation, a place to pause, breathe, and consider where the boundaries lie. Imagination is a beautiful thing, but it grows best when rooted in clarity. A good starting point is recognizing that quantum mechanics, despite its mystery, is a precise and disciplined framework. It describes how particles behave at tiny scales. It predicts the outcomes of experiments with extraordinary accuracy, and it does so without needing to reference thought, feeling, or subjective experience. Quantum mechanics explains the behavior of electrons in atoms, the structure of molecules, the way semiconductors work, and the physics behind lasers. What it does not do, at least not yet, is explain why you can taste chocolate, remember your first day of school, or feel the softness of a blanket. Quantum physics provides the ingredients, but consciousness is a dish prepared by systems far larger and more complex. One common misconception is that quantum mechanics magically solves the hard problem of consciousness, the puzzle of why subjective experience exists at all. While some theories explore the possibility that quantum processes might contribute to awareness, none of them provide a complete explanation. There is no quantum equation that produces sensation, memory, or self-awareness. Quantum effects may, at most, influence how the brain processes information, but the actual experience of being conscious remains a mystery that no physical theory, quantum or classical, has fully addressed. Another misconception is that quantum mechanics gives consciousness special powers. You sometimes hear claims that thoughts can directly influence physical reality at the quantum level, or that intention alone can collapse wave functions. These ideas may feel exciting, but they step outside what science supports. In physics, wave function collapse occurs through interaction, not mental effort. A stray photon, a vibrating molecule, or a passing electron can collapse a quantum state long before any person becomes aware of the system. Consciousness does not need to intervene. If human attention truly controlled quantum collapse, laboratory experiments would become very dramatic indeed, with results changing simply because researchers felt hopeful or distracted. Fortunately, the universe is more stable than that. A soft touch of humour helps here. If positive thinking alone could rearrange particle behaviour, your morning coffee might brew itself simply because you wished it into existence. Quantum buzzwords like manifesting or vibrating at a higher frequency would suddenly become rigorous scientific terms. But as charming as such possibilities sound, reality is a little more grounded. Thoughts influence actions, not photons. There is also the misconception that because quantum mechanics is mysterious, it can be invoked to explain anything mysterious. This is a gentle trap. Mystery does not automatically connect to mystery. Quantum physics is strange, yes, but in well-defined ways. Its uncertainties are mathematical, not mystical. Its puzzles arise from precise experimental findings, not from gaps in everyday understanding. Using quantum mechanics to explain consciousness without evidence risks turning a powerful scientific framework into a catch-all for speculation. It is the intellectual equivalent of using a microscope as a lampshade. Creative, but not especially helpful. Another area where care is needed is in the use of quantum language. Terms like superposition, entanglement, tunneling, or wave function collapse have specific meanings in physics. Outside their proper context, they can drift into metaphor. Metaphor is valuable, but it must be recognized as metaphor. Saying that the mind is in superposition when weighing options is poetic, not literal. Saying that relationships are entangled is symbolic, not scientific. These metaphors enrich conversation, but they should not be mistaken for explanations of neural mechanisms. The quantum mind also does not explain how large networks of neurons create coherent thoughts. Even if tiny quantum effects occur within neurons, bridging the gap from small-scale processes to large-scale experience remains challenging. Consciousness involves patterns of activity across billions of cells. It relies on electrical rhythms, chemical signals, memory consolidation, emotional regulation, sensory integration, and many layers of processing. None of these phenomena require quantum mechanics to function. They can be described effectively through classical biology and information theory. This does not mean that quantum processes are irrelevant to life. They shape chemistry, genetics, energy transfer, and many subtle biological interactions. Quantum biology is a growing field, revealing surprising quantum effects in plants, birds, and enzymes. But quantum contributions to life do not automatically extend to consciousness. Even if the brain uses quantum tricks at small scales, those tricks may support metabolism or signaling rather than thought or awareness. Another misconception arises from the idea that quantum uncertainty gives the mind complete freedom, removing the constraints of physical causation. But randomness is not the same as agency. If a choice were determined entirely by quantum randomness, it would not feel like your choice. It would feel like an unpredictable coin toss happening inside your brain. Free will, if it exists, likely emerges from complex neural dynamics rather than microscopic randomness. The richness of decision-making reflects the intricate interplay of memory, emotion, reasoning, and perception, not quantum fluctuations. Yet amidst these cautionary notes, imagination still matters. Creativity has always guided scientific discovery. Many breakthroughs begin as ideas that seem whimsical or speculative. The key is distinguishing what is speculation from what is evidence. Quantum consciousness theories offer intriguing possibilities, and they help scientists think about unexplored aspects of the mind. They open windows into new research on quantum biology, molecular dynamics, and information processing. They ask questions that encourage curiosity rather than closure. A gentle reminder helps keep the balance. It is possible to be inspired by the poetic resonance between quantum physics and consciousness without assuming that one directly explains the other. It is possible to explore imaginative theories without mistaking them for established science. It is possible to enjoy the metaphors without confusing them with mechanisms. The beauty of science lies in this balance, wonder shaped by evidence, imagination guided by clarity. Light humour can ease any lingering tension. Quantum consciousness sometimes attracts buzzwords like quantum healing, quantum energy fields, or quantum vibrations of thought. These phrases sound impressive, but often contain about as much scientific meaning as a cat wearing glasses. Cute, intriguing, but not especially informative. When quantum language is used responsibly, it is precise. When it becomes decorative, it drifts away from the science that gives it power. The gentlest, most important insight is this: the quantum mind hypothesis remains speculative. Some ideas are promising, others are unlikely, most are incomplete, but the curiosity behind them is valuable. Exploring these ideas pushes science to refine its understanding of both physics and consciousness. Even when the answers are uncertain, the questions help illuminate the landscape. What quantum mechanics does not explain is just as important as what it does. It does not explain subjective experience. It does not give consciousness magical powers. It does not provide shortcuts to understanding the mind. But it does inspire wonder, and that wonder can guide careful, thoughtful exploration. The challenge is to let imagination roam freely while keeping one foot gently anchored in what is known. In this balance between curiosity and clarity, both science and consciousness find their most meaningful growth. Studying quantum consciousness is a journey that continues to widen rather than narrow, a landscape where each discovery opens another path to explore. The field moves carefully, because the questions are delicate and the tools required to answer them are still growing into their full potential. There is something soothing about this slow pace, like watching a tide recede and reveal new shapes in the sand. Progress arrives in small, thoughtful steps, guided by curiosity rather than urgency. The next generation of tools for studying the brain will reshape what scientists can observe. Modern neuroscience relies on imaging that captures electrical signals, chemical traces, and large-scale patterns of activity. These methods reveal how neurons fire and how networks synchronize, but they do not yet reach deeply enough into the molecular world where potential quantum effects might hide. Future instruments may be able to follow individual molecules as they shift, fold, and interact within living neurons, They may let researchers watch tiny cellular structures move in real time, or detect subtle changes in electromagnetic fields generated by groups of molecules. Quantum sensors are one promising development. These sensors are being designed to detect incredibly small variations in magnetic and electric fields, far more sensitive than anything currently available in biological research. If they continue to improve, they might allow scientists to observe the delicate electrical environment inside neurons. A single ion drifting across a membrane could leave a trace. A flicker of current in a microscopic channel might become visible. If quantum effects influence these processes, these sensors may one day capture their signatures. Ultrafast spectroscopy offers another window. This technique uses pulses of light that last only trillionths of a second, short enough to track chemical reactions as they unfold. Researchers have already used it to observe quantum coherence in photosynthesis, and similar methods may help reveal whether brief pockets of coherence appear within the brain's molecular structures. Even if coherence lasts only for fleeting moments, those moments might still reveal something meaningful about how biological systems manage energy or information. The challenge is adapting these methods to living tissue without disturbing the processes being measured. That challenge is slowly being met as the tools become gentler and more precise. There is also growing interest in nanoscale probes that can travel through cells without damaging them. These probes could watch how proteins and microstructures behave while neurons fire, moving almost like miniature reporters inside the brain's crowded interior. They might detect movements or vibrations too small for current imaging methods, revealing patterns invisible from the outside. If quantum tunneling or other quantum behaviors influence these molecular events, these probes could provide the first direct evidence. With these tools, scientists will be able to design experiments that test some of the most intriguing questions in the field. One question is whether coherence can persist inside biological structures long enough to matter. Experiments might isolate specific proteins or cellular scaffolds and examine how they behave under conditions that mimic the interior of living cells. If coherence appears, the next step would be to study how it changes with temperature, molecular motion, or electrical activity. Another question is whether tunneling plays a significant role in how neurons signal. Ion channels are narrow passageways, and the movement of particles through them can be sensitive to quantum effects. Experiments could measure how ions behave under precisely controlled conditions, comparing classical predictions with observed behavior. If tunneling influences timing or efficiency, it could shape how networks synchronize their activity. There's also the question of entanglement in biological systems. Detecting entanglement in living tissue would require extraordinary precision because biological environments are noisy, warm, and constantly changing. Still, researchers are developing methods that may eventually test whether molecular structures exhibit quantum correlations stronger than classical physics can explain. Even limited evidence of such correlations would reshape how scientists think about biological complexity. These experiments will not arrive overnight. The tools needed to detect quantum behavior in biological systems are at the edge of what modern technology can achieve. They demand sensitivity, stability, and precision rarely found in the study of living tissue. But progress tends to accumulate quietly. A small improvement in sensor stability, a new way to cool equipment, a refined algorithm for analyzing data. All of these help build the foundation for experiments that once seemed impossible. Theoretical work will grow alongside experimental work. Physicists and neuroscientists will continue refining models showing how quantum effects could influence biological processes and which effects are unlikely. These models will help guide experiments, offering predictions that can be tested. They will also help separate ideas with genuine scientific potential from those that drift too far from what is known. As theories improve, They may reveal subtle ways that quantum behavior shapes molecular dynamics without claiming to solve the mystery of consciousness itself. Artificial intelligence may contribute as well. As machine learning systems become better at modeling complex networks, they may help scientists understand how information flows through the brain, how patterns arise from many interacting components, and how small-scale variations can influence large-scale function. These insights may help show whether quantum processes offer advantages beyond classical ones, or whether classical dynamics alone can explain the richness of cognitive experience. Through all of this, the study of quantum consciousness will remain grounded in careful observation rather than bold claims. Researchers will need to protect clarity while allowing imagination the space to explore. The field benefits from open-mindedness, but it grows only when evidence guides the way. The slow pace is not a sign of stagnation. It is a sign of respect for the complexity of both physics and biology. There is something soothing about imagining how this research might unfold over the next several decades. Laboratories filled with quiet hums of equipment, scientists peering through instruments designed to reveal structures smaller than wavelengths of light, tiny signals emerging from noisy data, pointing toward possibilities that require patience to understand. The search for quantum contributions to consciousness may not lead to dramatic revelations, but it will deepen our understanding of life's building blocks and the processes that shape awareness. And if future studies ever reveal a small but meaningful quantum contribution to thought, it will not be because consciousness was pulled out of thin air. It will be because researchers measured something subtle, something fleeting, something that had always been there, quietly influencing the ways molecules behave. If no such contribution is found, that result will be equally valuable because it will clarify where to focus attention next. Either way, the exploration continues. Quantum mechanics will keep offering surprises, neuroscience will keep uncovering layers of complexity. Technology will keep pushing the boundaries of what can be seen and measured. Each advance will help illuminate the connection between the microscopic world and the landscape of consciousness. The future of studying quantum consciousness is not a single destination, but a gradual unfolding of insight, shaped by curiosity and guided by careful evidence. It invites us to keep wondering, to keep listening, and to remain open to possibilities that shimmer just beyond our current understanding. Consciousness is something lived from within, and even after exploring its quantum possibilities, it remains one of the most quietly astonishing features of being alive. You can examine neurons, measure electrical pulses, trace the flow of information, and even peer into the strange, probabilistic world of quantum mechanics. Yet the feeling of awareness continues to hover just beyond the reach of full explanation. Not in a troubling way, but in a way that invites reflection. Looking closely at consciousness through both microscopic and cosmic lenses reveals how remarkable it is that awareness emerges at all. Matter follows physical laws, atoms bind into molecules, and molecules build the intricate architecture of living cells. Out of these processes, patterns form and shift. Networks of neurons begin to coordinate. Information loops and reorganizes. Somewhere along this unfolding, experience appears. The sensation of warmth, the lift of a memory, the quiet drift of a thought. No single scientific theory explains why these patterns feel like anything from the inside, and that gentle gap is part of the mystery's charm. Quantum mechanics adds a different texture to the story. It shows a universe where certainty softens, where possibilities overlap before settling into an outcome. Whether or not consciousness draws upon these behaviors directly, it exists within a reality shaped by them. Atoms behave the way they do because of quantum rules. Chemistry relies on the quantist nature of energy. Life grows from these foundations, and consciousness grows from life. Quantum physics may not reveal why awareness arises, but it frames the conditions that allow something as intricate as a mind to form. The study of quantum consciousness will likely progress gradually, guided by patient experimentation and better tools. Future instruments may allow scientists to observe the brain with astonishing precision, revealing movements and interactions that are invisible today. Some experiments will test whether quantum effects influence molecular behavior inside neurons. Others will examine whether coherence or tunneling plays any meaningful role in neural signaling. Each result, even the quiet ones, will refine our understanding of how the brain works. This exploration matters not because it promises a single sweeping answer, but because it encourages thoughtful investigation. It strengthens connections between physics, biology, and philosophy. It expands the range of questions researchers are willing to ask. Whether quantum processes shape consciousness or not, the search deepens our understanding of both the mind and the physical world it inhabits. Yet beyond the science lies the simple truth that consciousness is experienced directly. You do not need a theory to feel present. You do not need an equation to appreciate the way a moment settles softly into memory. Whatever its origin, awareness is the medium through which life unfolds. It colours every sensation, thought, and emotion. Understanding its mechanisms may grow clearer with time, but the worth of experience itself does not depend on that clarity. There is a quiet comfort in allowing consciousness to remain partly mysterious. It is something you can study, imagine, and feel all at once. The lack of a complete explanation does not diminish its depth, it enriches it. Even in a universe governed by elegant and sometimes bewildering laws, there is room for gentleness, curiosity, and wonder. Quantum or not, consciousness remains one of the most beautiful expressions of the universe's ability to organize itself into something capable of noticing, reflecting, and understanding.